Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. At the precipice of a cosmic abyss, time itself seems to falter. In the darkness ahead, starlight stretches and contorts, swirling into a silent maelstrom. We find ourselves at the edge of a black hole, a place where gravity conquers light and time. The very fabric of reality is pulled thin. Moments elongate and dance on the event horizon. Space twists like a funhouse mirror, reflecting distorted images of the universe back at us. A brilliant halo encircles the void, the last light of doomed matter painting a ring of fire around an inky circle of nothingness. Here, in this theater of extremes, we hover on the brink of the known and the unknown. Our senses strain to comprehend what lies before us. The glow from the accretion disk, superheated gas spiraling down the drain of space, bathes us in ghostly brilliance. Beyond that luminous ring, there is no light at all. Tendrils of darkness reach out, gripping every photon that strays too close, swallowing even the colors of the sky. The black hole's gravity wells up like an ocean wave about to break, and we are at its crest. Time itself is unsteady. A second here might be eons elsewhere. We feel the weight of eternity in the slowing of our own heartbeat. Each tick of a clock stretches, seconds becoming hours, hours becoming years, as though the cosmos is holding its breath. Listen closely. The silence is paradoxically loud. We cannot hear the chaotic inferno of the accretion disk, but we can feel its violence in the vibrations of space around us. If we focus, perhaps we sense a faint tremor, the distant echo of space-time itself ringing as matter plunges inward. The black hole's event horizon, the invisible boundary before us, is both gateway and wall. Cross it, and all return is cut off. It is a one-way door to oblivion. Yet at this boundary, physics as we know it begins to fray. Up is meaningless, down is inevitable, forward might be into the past. The compass of reality loses direction. We float at this edge like a wary traveler at the rim of a bottomless chasm. Emotions swell in the face of such majesty and terror. Awe, as we witness stars being shredded into glowing ribbons, spiraling in surrender. Fear, as we ponder that a step closer would pull us irrevocably in. And wonder, deep, childlike wonder, at confronting something so absolute, so final. It's as if we've approached the throne of a cosmic deity, one that rules with both creation and destruction. Creation of energy flares and new beginnings in the jets that burst outward, and destruction of whatever falls prey to its grip. In this suspended moment, time slows nearly to a stop. We recall the stories of adventurers and scientists who dared to imagine this very scene long before any human eyes saw it. The black hole's shadow looms large in our view, a circle of pure night encased in swirling light. It challenges us, beckons us to understand. We stand at the threshold of a black hole, on the edge of forever, where all we know teeters on the brink of all we cannot yet fathom. Despite the danger, curiosity propels us. We begin the journey to unravel how such a place came to be, and what it means for our universe. Our understanding of these cosmic abysses was not born overnight. It began as a whisper centuries ago, in an age when the only gravity known was that which pulled apples from trees and guided planets on their orbits. A few bold thinkers imagined something radical, a star so massive, so dense, that not even light could escape its grasp. They spoke of dark stars hidden in the fabric of space, bodies that would trap light itself. This idea, daring and strange, flickered briefly in the late 18th century and then dimmed. The world was not yet ready to confront such darkness. For more than 100 years, the concept lay dormant, half forgotten, like a fairy tale too grim to tell. But at the dawn of the 20th century, a new understanding of gravity emerged. A brilliant reimagining of space and time revealed that gravity was not just a pull, but a warp in the cosmic fabric. Space could bend, time could stretch, and the paths of light could curve through the heavens. Within the equations of this new theory, quietly tucked away, was the blueprint for a black hole. A German scientist solving those equations during a time of great turmoil found that if matter were crushed tightly enough, it would carve a hole in space-time, an event horizon beyond which none could return. The mathematics was clear and unforgiving, characterizing a cosmic trap hidden in the equations of general relativity. Yet even with the math in hand, many scientists recoiled. The notion seemed absurd. Could nature truly create a singularity, an infinite descent into darkness? The great minds of the time believed something would surely intervene to prevent such an extreme. For decades, black holes were treated as exotic math puzzles, not physical objects. They were the dragons at the edge of our maps of understanding, perhaps possible on paper, but surely not out there in the starry skies. It took the relentless collapse of a dying star in theory to change minds. In the midst of a world war and its aftermath, a few researchers calculated what might happen when a massive star's life comes to an end. They realized that if a star were heavy enough, no known force could halt its collapse. The star would continue imploding, crushing itself past any point of return. In that silent theoretical collapse, the first realistic portrait of a black hole was sketched. Still, the idea remained academic, a curiosity rather than an impending reality. The true turning point arrived with observations that defied all other explanations. Around the time humanity first launched satellites and new telescopes into space, the sky revealed strange phenomena. Quasars, quasi-stellar objects, were discovered pouring out more light than 1,000 galaxies from a tiny point. What engine could drive such brilliance? Nothing known could do that. Nothing except the gravity of a supermassive black hole devouring matter at the heart of a young galaxy. Around the same era, astronomers found an X-ray beacon in the constellation of the Swan, a bright, flickering glow that seemed to emanate from empty space. Careful measurements showed a visible star circling an invisible companion, tugged around by an object with immense mass packed into zero visible volume. It was as if an unseen phantom were whipping a star around like a weight on a string. This was the first strong evidence that black holes were not just theoretical. They were out there, lurking in our cosmic neighborhood. As evidence mounted, the scientific community underwent a profound shift. In the later decades of the 20th century, these objects went from speculative to central in astrophysics. The term black hole itself, coined around that time, captured the public imagination and the scientific reality, an inky hole in space that not even light can escape. By the late 20th century, what was once laughed off as a mere mathematical oddity had become an accepted part of the cosmic menagerie. Observations of stars at the centers of galaxies, whipping around unseen masses, indicated that something colossal and dark anchored them. One by one, the pieces fell into place. Almost every large galaxy seemed to harbor a monstrous black hole in its core, and smaller stellar mass black holes dotted the Milky Way, like hidden tombstones of long-dead stars. By the turn of the millennium, black holes were no longer fringe ideas. They were frontiers of exploration. We had begun detecting the very tremors of space produced when two black holes collide, and even imaging the silhouette of a black hole against a glowing cosmic backdrop. In just a few human generations, the concept journeyed from whimsical conjecture to concrete observation. Our ancestors imagined the possibility. Our parents' generation debated their reality. And in our time, we have come face to face with the dark heart of a galaxy, proving once and for all that these cosmic abysses are real. Each step of this historical journey, from the first whisper of a dark star to the bending of light in a revolutionary theory of gravity, to the discovery of celestial X-ray wraiths and blazing quasars, has been a rung on a ladder of revelation. And as we climbed that ladder, we moved closer and closer to the edge of the black hole itself. Now, standing here at this precipice, we carry with us the legacy of those insights and the awe of knowing that not only do black holes exist, but they are an integral part of our cosmic story. Now that science had accepted these entities as real, another question remained. What exactly is a black hole? At first glance, it seems to defy understanding, a whole rather than an object. But we can break down this enigma into parts, as one might describe the body of some mythical beast. The outermost surface of a black hole is not a tangible surface at all, but an invisible boundary known as the event horizon. This is the famous point of no return. It is the edge beyond which freedom ceases to exist. If anything, a star, a spacecraft, or even a ray of light ventures closer than this boundary, it will never re-emerge. To escape from that point would require moving faster than light itself, a feat the universe forbids. So the event horizon is like a one-way membrane in space. Things can fall in, but nothing comes out. To an outside observer, it appears as a perfect black sphere, a shadow where no light comes from. In truth, it isn't a physical surface, but a region of space defining where the pull becomes inescapable. Imagine the event horizon as the mouth of a great cosmic whirlpool. Just as water in a whirlpool spirals inward and cannot reverse course once it's too close to the drain, anything near a black hole spirals past this horizon and is swallowed. The closer you get, the stronger the pull. At a certain distance, that pull becomes absolute. This distance scales with the black hole's mass. A black hole 10 times the sun's mass has an event horizon only a few tens of kilometers across, whereas a black hole, millions of times the sun's mass, has a horizon that spans millions of kilometers. For perspective, a monster black hole can have an event horizon larger than our entire solar system. And yet, all that volume leads to something astonishingly small at the center. Deep inside, at the very core of a black hole, lies the singularity. This is the ultimate abyss, the heart of darkness, where density becomes infinite by our current understanding. Picture all the mass of a star, or even millions of stars, crushed into a point with no size. It's a place where our familiar ideas of space and time break down completely. In a non-spinning black hole, this singularity would be an infinitesimal dot. In a spinning black hole, it might be stretched into a tiny ring. Either way, it is hidden behind the curtain of the event horizon, forever out of direct sight. The singularity is like the secret at the black hole's center, a secret we cannot peek at because nature has drawn a veil over it. All we know is that it's where gravity has reached its crescendo, an infinity in a finite space. Between the event horizon and the singularity lies the black hole's interior, a one-way tunnel of sorts. Contrary to what one might expect, if you were falling in, you wouldn't actually see anything special as you pass the event horizon, at least not for a very large black hole. There is no sudden change in scenery, no shimmering wall. Locally, the laws of physics feel normal at the horizon. It's only once well inside that the space-time curvature becomes lethal. To any distant observer watching you fall, however, something very different happens. They would see you slow down and fade, never quite crossing the horizon, your image red-shifted to black. The event horizon is as much a divide in time as in space. From the outside, it seems to freeze moments on its edge for eternity. The black hole's event horizon can be thought of as a spherical prison. It holds within it everything that has ever fallen past, all the mass and information trapped like flies in amber on its boundary. Incredibly, a black hole can be completely described, as far as the outside world is concerned, by just a few numbers. Its mass, its spin, rotation, and perhaps an electric charge, though astrophysical black holes are expected to be essentially uncharged. Aside from those, a black hole carries no visible imprint of what fell into it. It does not remember whether it devoured a star, a planet, or a cloud of gas. All those details are lost behind the horizon. The beast has no hair, as physicists say, no distinguishing marks beyond its basic parameters. This simplicity is both elegant and eerie. It's as if the black hole digests everything into the same featureless state. The event horizon's size grows with each meal, like a belly expanding, but no other trace remains. Inside the horizon, space and time themselves trade roles. The pull inward isn't just a force, it becomes your future. Just as every next second of your life must carry you forward in time, every step you take inside a black hole must carry you further inward. There is no stopping, no standing still. The singularity lies in your future, as inevitably as tomorrow. This is perhaps the strangest aspect of black hole anatomy. Once inside, falling to the center is as inescapable as time flowing forward. The geometry of space-time warps so extremely that every direction you could possibly move ultimately points you toward that central collapse. In sum, the anatomy of a black hole consists of an outer boundary where the world stops making sense to the rest of the universe, and an interior where the world stops making sense, period. A horizon where you vanish from the view of others, and a singularity where known laws of nature vanish from view. Between them, a warping labyrinth of space and time. It's a cosmic trapdoor. Below it, we cannot see. Beyond it, we cannot return. Yet this trapdoor is a fundamental part of our universe. From outside, it creates some of the most wondrous and terrifying phenomena we can observe. To truly know a black hole, we must understand both its unforgiving simplicity and its capacity to challenge reality at the deepest level. Every black hole has an origin story. For the most common black holes, those only a few times more massive than our Sun, the story begins with the death of a star. Picture a star perhaps 20 or 30 times the mass of the Sun, burning brightly for millions of years. Deep in its core, nuclear fusion fights a battle against gravity, generating light and heat that push outward and hold the star up. But eventually, even the mightiest star runs out of fuel. The furnace at the center flickers out, and outward pressure fades. In that instant, gravity, which had been patiently waiting, seizes the advantage. The star's core collapses inward in a fraction of a second. Matter rushes toward the center at incredible speeds. The collapse is so violent and sudden that it triggers a colossal explosion, a supernova. The outer layers of the star are blasted into space, shining as bright as a billion suns for a brief moment. But at the heart of this cataclysm, something even more remarkable happens. The core continues to collapse, tighter and tighter, until it forms a black hole. This newborn black hole might be only tens of kilometers across, even though it contains a mass equivalent to several suns. Imagine an object with the mass of our Sun squeezed into a sphere the size of a city. The gravity of this remnant is intense. It's as if the death of the star punches a hole in the fabric of the universe. What remains is an ultra-dense corpse, a stellar mass black hole, left behind in the aftermath of the supernova's fury. In some cases, if the star was extremely massive or conditions are just right, the collapse may occur so fast that much of the star falls directly into the black hole without a supernova bang. A quiet death, forming a black hole in silence and darkness. These stellar mass black holes are scattered throughout galaxies like ours. In the Milky Way alone, astronomers estimate there could be tens of millions of them, hidden in the darkness. Most wander unseen, cold and quiet, because contrary to popular imagination, a black hole that is not actively feeding is essentially invisible. It doesn't glow or suck things in like a vacuum cleaner from afar. A lone black hole in empty space would be one of the most unassuming objects, undetectable to our telescopes, save for its gravitational pull. It's only when they interact with other objects that we notice their presence. Often, a stellar black hole reveals itself when it has a companion, say, another star orbiting it. If the two are close enough, the black hole's gravity can siphon gas from its stellar partner, drawing a stream of matter into its grasp. This gas spirals in, forming a swirling accretion disk around the black hole and heating up to extreme temperatures. In X-ray light, such a system blazes brilliantly. From Earth, we see these X-ray binaries as flickering beacons. It was in this manner that the first stellar black holes were confirmed, a visible star orbiting an unseen massive companion, its gas being inexorably pulled away and eaten. As that gas falls in, it lights up, crying out the presence of the invisible devourer. Within that disk, and near the black hole's edge, extraordinary processes occur. The intense gravity pulls one side of an infalling object harder than the other, a tidal force that can stretch objects into long strands. If an unlucky star or planet ventures too close to a stellar mass black hole, it could be pulled into a thin stream, a process poetically called spaghettification. The difference in gravity between the side of the object nearer the black hole and the side farther away is so great that it rips the object apart, stretching it as it goes. Fortunately, such extreme encounters are rare on human timescales, but they remind us how deadly these small black holes can be in close quarters. Stellar black holes may be small compared to their supermassive cousins, but they are by no means trivial. They pack tremendous gravity in a tiny package and can have profound effects on their surroundings. When two of them are born in a binary pair of stars, their deaths can lead to a spectacular reunion. The two black holes themselves can eventually spiral toward each other and merge in a violent embrace, shaking the fabric of the universe with gravitational waves. Such mergers momentarily produce more power than all the stars in the observable universe combined, though in gravitational energy rather than light. We'll hear more about those cosmic ripples later, but it is these stellar mass black holes dancing and colliding that have given us an entirely new way to observe the universe. In the grand tapestry of the cosmos, stellar mass black holes are like the ashes left after a great fire, the remnants of once brilliant stars. They mark the endpoints of stellar evolution and seed the galaxy with extremes of gravity. Each is a silent testament to a star that lived, shone, and died in a dramatic finale. They also serve as the starting point for a black hole's life. Given the right circumstances, a stellar black hole can gather more mass and grow, potentially merging with others to become something larger. But even on their own, these dark stellar remnants are fascinating and fearsome. They are, after all, direct connections to one of the most violent events in nature, a star's final collapse, and they embody the concept of death, giving rise to something new and strange. If stellar mass black holes are the ashes of individual stars, supermassive black holes are the colossal giants that reign over galaxies. These behemoths, found in the hearts of most galaxies including our own, contain millions to billions of times the mass of the Sun. Imagine something as heavy as an entire cluster of stars, all condensed into a region smaller than our solar system. These black holes are on a different scale altogether. They are cosmic anchors, so massive that their gravity binds whole galaxies. Stars in a galaxy's core swirl around an unseen center at astonishing speeds, compelled by the gravitational grip of a supermassive black hole lurking there. Our own Milky Way harbors such a monster at its nucleus. It's relatively modest as supermassive black holes go, about 4 million suns worth of mass. We cannot see it directly with our eyes, but we see the dance of stars around an apparently empty spot. Those stars whip around at velocities of thousands of kilometers per second, tracing orbits that betray an incredibly dense mass within. It's like watching leaves swirled by an invisible whirlpool. From their motion, we infer the whirlpool's presence. Occasionally, that dark center awakens. Bursts of high-energy flares have been observed when small clouds of gas or errant stars wander too near and get torn apart, feeding the beast and causing it to flicker in X-rays and infrared light. In other galaxies, the supermassive black holes are even larger and more voracious. The most massive black hole known weighs tens of billions of solar masses and would dwarf our entire solar system many times over. When such giants actively devour matter, they become the brightest objects in the universe. Paradoxical as it sounds, nothing is brighter than a feeding black hole. As gas and dust spiral into a supermassive black hole's maw, they heat up and blaze with light visible across billions of light years. This is the engine behind quasars and active galactic nuclei, those brilliant beacons at the cores of distant galaxies. In the early epochs of the universe, quasars shone like cosmic lighthouses, powered by supermassive black holes consuming matter at ferocious rates. They can outshine their entire host galaxies, a tiny central point releasing more light than the billions of stars around them combined. How does a black hole grow so big? It's a bit of a cosmic mystery, one that scientists are still piecing together. Some supermassive black holes likely began as smaller, stellar mass black holes that merged and swallowed gas over billions of years, gradually ballooning in mass. Galaxies often collide and merge with each other, and when they do, their central black holes can also coalesce, combining their mass. Over cosmic time, through galactic marriages and steady feeding, a black hole can climb the mass ladder into the supermassive range. However, we have observed quasars less than 1 billion years after the Big Bang that already house black holes of billions of solar masses. That is a very short time, cosmically speaking, for something to grow so large. It suggests that some black holes had a head start. Perhaps they were born big, formed by the direct collapse of enormous primordial gas clouds, or as the remnants of the very first generation of supermassive stars that lived fast and died young. It's possible that in the early universe, conditions allowed the creation of seed black holes much larger than any single star, giving them a running start. Once a supermassive black hole exists, it becomes a central player in its galaxy's evolution. It doesn't just sit quietly. Even when not actively gobbling matter as a quasar, its presence can influence star formation and the dynamics of the galaxy. It acts as a sort of cosmic governor. When it feeds, it can erupt in jets and winds, which we'll explore soon, pumping energy back into the galaxy. These outflows can heat up or blow away the gas that would otherwise form new stars, thereby regulating the galaxy's growth. In this way, the black hole at the center and the galaxy around it seem to grow in tandem, each influencing the other. Astronomers have discovered an intriguing relationship. The mass of a galaxy's central black hole is roughly proportional to the mass of the galaxy's central bulge of stars. They scale together, as if the black hole and the galaxy have been co-authoring a story over eons, keeping each other in check. Supermassive black holes are, in many ways, cosmic paradoxes. They are enormously destructive. Any star that ventures too close can be ripped apart. Any gas cloud will be consumed. Yet, in their destruction, they create. The energy they release can trigger shocks in distant gas clouds, sometimes compressing them enough to spark the birth of new stars at a galaxy's outskirts. They shape the structure and fate of galaxies. In their quiet phases, they are dark and undetectable. In their active phases, they are the brightest beacons in existence. They sit at the centers of galaxies for billions of years, like silent puppet masters orchestrating cosmic dramas. Each one is a reminder that in the universe, sometimes the most powerful furnace of energy is not a shining star, but a dark pit that paradoxically radiates brilliance when the time comes to feed. Not all black holes fit neatly into the categories of stellar or supermassive. Astronomers have long suspected the existence of black holes that are in between, the so-called intermediate mass black holes. These would weigh perhaps a few hundred to a few 100,000 suns, bridging the gap between the star-sized corpses and the galactic giants. For decades, they remained elusive, like phantom missing links in the cosmic record. If they exist, They might hide in the centers of globular clusters, spherical swarms of stars, or as the remnants of mini-galaxies that merged into bigger ones. There have been tantalizing hints. A powerful X-ray flare in a distant galaxy that suggested an object of about 50,000 solar masses tearing apart a star. Stars in certain dense clusters moving in ways that hinted at an unseen massive presence at the core. One by one, these clues have emerged, but definitive proof has been hard to pin down. Intermediate black holes are shy, revealing themselves only subtly. The universe, however, gave us a nudge in recent years. When observatories on Earth began to listen to the universe using gravitational waves, ripples in space-time, we detected the collisions of stellar mass black holes by the dozen. In one such cataclysmic event, two hefty black holes merged and formed a new black hole heavier than any single star's collapse could produce, an object of about 150 solar masses. For a moment, we had direct evidence of an intermediate mass black hole born from the union of smaller ones. It was a brief glimpse. The merger itself was over in seconds and the waves faded, but it confirmed that nature can make black holes in this mass range. The question remains, do intermediate black holes persist independently in the universe, slowly grown over time, or are they mostly stepping stones, formed in rare mergers and destined either to keep growing or to stay hidden in remote corners? Scientists continue to hunt for these middling monsters. Each candidate sighting, perhaps a peculiar source of radiation or a gravitational lensing effect on background starlight, brings hope that we will finally catch one in the act of simply being itself, neither small nor supermassive, but something intriguingly in between. Now pivot from the present back to the very beginning of time. There is another hypothetical class of black holes, even more mysterious and elusive: primordial black holes. These would not come from stars at all, but from the high-energy, high-density chaos of the early universe itself. In the first second after the Big Bang, the universe was an extremely hot soup of energy and particles. Tiny fluctuations in density, quantum wrinkles in the fabric of the young cosmos, could have been magnified during cosmic inflation, the rapid expansion at the universe's dawn. In some regions, the concentration of matter might have crossed a critical threshold, collapsing into black holes mere moments after time began. These primordial black holes could, in theory, have had masses ranging from tiny fractions of a gram to thousands of suns, depending on the size of the fluctuation that birthed them. Imagine black holes as small as mountains, or even asteroids zipping through the cosmos. Some might have been so low in mass that over billions of years they would entirely evaporate via Hawking radiation, a process we'll discuss later. Heavier ones could survive to the present day, scattered throughout space as fossil relics of the Big Bang. Primordial black holes offer a tempting explanation for some of our universe's puzzles. Could they be a component of the dark matter that makes up much of the universe's mass? If so, swarms of unseen primordial black holes might be drifting through galaxies, each too faint to notice individually, but collectively exerting gravitational influence. Researchers have looked for signs of them, flashes of light from a tiny black hole evaporating at the end of its life, or subtle gravitational lensing events when one passes in front of distant stars. So far, these searches have come up empty or inconclusive, placing limits on how many primordial black holes could exist and in what mass ranges. If very small ones had formed, most would be gone by now, having evaporated in a final burst of gamma rays. If medium-sized ones had formed, they cannot be too numerous, or we would have seen their effects on Starlight statistically. The possibility remains that primordial black holes might exist in a narrow range of masses, quietly contributing to the dark matter. It's a fascinating idea that alongside particles and atoms, some portion of the unseen mass of the universe could actually be an ancient population of black holes. Both intermediate mass and primordial black holes highlight how much we still have to learn. Intermediate black holes challenge us to find objects that are neither the result of a single star's death nor the long-cultivated giants in galactic centers. but something formed by unique circumstances. Perhaps the merger of many stars or black holes in a dense cluster, or the direct collapse of a massive early star that wasn't quite a galaxy's nucleus. Primordial black holes, on the other hand, challenge our understanding of the early universe. They ask whether nature forged black holes before stars even existed. If they did, then black holes might predate galaxies themselves, sprinkling the cosmos with gravitational traps from time immemorial. These lesser-seen members of the black hole family, if they exist in abundance, could fill important chapters in the story of our universe. Intermediate black holes might explain how the supermassive ones got such a jumpstart, perhaps serving as the seeds that grew into quasars. Primordial black holes could rewrite our theories of cosmology and dark matter. As of now, they remain subjects of intrigue and investigation. They remind us that not all black holes announce themselves readily. Some lurk in mass ranges or epochs that we have only begun to explore. The cosmic story of black holes is far from complete. There are still shadowy characters that may yet emerge from obscurity. So far, we've considered black holes themselves, what they are, where they come from. But black holes do not live in isolation. Their presence dramatically affects their surroundings. When they feed, they often become the centers of the most radiant displays in the universe. The key lies in the accretion disk, the maelstrom of matter that gathers around a black hole as it pulls in gas, dust, or the occasional star. As material falls toward a black hole, it is forced into a spiraling orbit, like water circling a drain. This creates a flattened disk of orbiting debris around the black hole. The closer the matter gets to the black hole, the faster it races, whipping around at a significant fraction of light speed. Friction and turbulence in the disk heat it to extraordinary temperatures. What was once cold interstellar gas or a star's outer layers becomes a ferocious plasma tens of millions of degrees hot. At such temperatures, it glows fiercely, typically in high-energy light like X-rays and ultraviolet. Paradoxically, a feeding black hole is often surrounded by a blaze of light. We don't see the black hole itself, but we see this brilliant last gasp of material as it struggles to hang on before crossing the horizon. Imagine looking at a black hole being fed by a stream of gas from a nearby star. You would see a glowing disk encircling a dark center. The inner edge of the disk orbits so fast and is so distorted by gravity that its light is bizarrely stretched and bent. On one side of the disk, where the orbiting material comes toward us, the light is boosted, blue-shifted, and bright. On the opposite side, where it moves away, the light is weakened, red-shifted, and dimmer. This asymmetry can actually be observed, a gravitational fingerprint on the disk's light. Above and below the disk, the black hole's gravity warps photons into a halo or ring, the photon ring, a circular image of light that skims just outside the event horizon and swings around. Together, the disk and these warped pathways of light create an image of a glowing donut-like structure, a beacon signaling a black hole's presence. But the drama doesn't end with the disk. In many cases, especially with supermassive black holes, twin jets are launched, colossal, narrow beams of particles and energy that shoot out from the poles of the black hole's spinning disk. These jets are like cosmic blowtorches drilling through space. They can extend for thousands, even millions of light years, far beyond their host galaxy's bounds. To put that in perspective, a jet from a galaxy's center can be so large that, if we could see radio waves with our eyes, it would span the sky, even though it originates in a nucleus millions of light years away. These jets contain matter accelerated to near light speed, hence relativistic jets. They are composed of charged particles, electrons and heavier nuclei, or perhaps electron-positron plasmas, and are threaded by intense magnetic fields. The prevailing theory is that the rotation of the black hole and the disk's magnetic fields can fling some of the infalling matter back out, turning it into twin jets that blaze out along the axis of rotation. The physics at the base of these jets is complex, but we can appreciate the outcome. A black hole can both devour matter and spit some of it back out in dramatically transformed fashion. The jets shine in radio waves, X-rays, and gamma rays. In fact, some of the brightest radio sources in the sky are the lobes of energized gas at the ends of these jets, where they ram into intergalactic material and deposit their energy. It's a bit like a fire hose blasting into a pool of water. Where the stream hits, great billows form, radio lobes, that mark where the jet dumps its power. Accretion disks and jets are not just showpieces. They play a crucial role in the cosmic ecosystem. The disk is the black hole's dining table, and how fast a black hole grows is determined by how much matter the disk funnels in. Disks can flicker and flare when chunks of matter fall in, giving astronomers a way to track the feeding habits of black holes. Jets, on the other hand, carry away tremendous energy and momentum. They can heat up the surrounding gas for hundreds of thousands of light years, even stopping new stars from forming by blowing out or heating the raw material. Alternatively, the shock of a jet blasting into gas clouds can compress them and induce new starbirth at the edges. In either case, jets mean that a black hole's influence isn't confined to its immediate neighborhood. It can reach far beyond, affecting the fate of its galaxy and even the environment of intergalactic space. From a storytelling perspective, it's as if the black hole has two faces: the gluttonous eater, the accretion disk, that glows from the feast, and the mighty dragon, the jets, that breathes fire back into the cosmos. Amazingly, we have actually photographed something akin to that eater's face. The first image of a black hole's immediate vicinity showed a bright ring, the glow of the disk and the photon ring, outlining the silhouette of the black hole itself. It was light from an accretion disk, 55 million light-years away, that provided the ink to sketch the portrait of that black hole's shadow. As for jets, we have imaged those too. For instance, the supermassive black hole in that very galaxy we photographed has a jet visible as a bright streak shooting out from the galaxy's core in radiolight. Accretion disks and jets turn black holes from silent gobblers into cosmic performers. They ensure that even as a black hole cloaks itself in darkness, the act of feeding breaks that silence with radiant energy and astonishing dynamism. It's a spectacle of creation and destruction entwined, matter falling in to be destroyed, energy flung out to perhaps create anew elsewhere. In the grandeur of a galaxy, the brightest core and the longest jets both proclaim the presence of a once invisible singularity, making itself known by the havoc and brilliance it unleashes. Black holes may be small compared to their host galaxies, but they wield influence far beyond their size. In the cosmic ecosystem, a supermassive black hole at a galaxy's core can function like a regulator, sometimes a nurturer, other times an executioner of star formation. It is astonishing to realize that an object which occupies a tiny fraction of the galaxy's volume can govern the fate of billions of stars spread across tens of thousands of light years. Yet through energy and gravity, it does. When a supermassive black hole feeds ravenously, it enters what we call an active phase. The accretion disk and jets we discussed pump out stupendous amounts of energy into the galaxy's innards. This outpouring acts like a cosmic wind or heater. Gas that would have cooled and condensed into new stars can instead be blown outward or warmed so much that it cannot clump to form stars. Think of a gardener burning dry leaves. The smoke drives away insects and seeds alike. Similarly, the feedback from a quasar, an active black hole, can clear out a galaxy's stellar nurseries. Whole reservoirs of gas get ejected into intergalactic space, or stirred so violently that they remain too hot to collapse into stars. The result? The galaxy's prolific starbirth is quenched. It ages. Its existing stars grow old and red, with few new ones to take their place. Many giant elliptical galaxies, immense balls of old red stars, likely had such a phase in their youth. Their central black holes ignited and effectively said, No more stars shall form here, rendering them red and dead galaxies by cosmic middle age. On the flip side, black hole influence isn't purely destructive. The energy blast from a central black hole can also compress gas in certain regions, triggering bursts of star formation just outside the affected zone. It's as if the same gardener prunes in one place but scatters fertilizer in another. Observations show instances of new stars blooming at the edges of cavities carved out by black hole-driven winds in galaxies and galaxy clusters. The interplay is complex. Depending on the galaxy's size, the black hole's power, and the distribution of gas, the outcome can be a balance between suppressed starbirth in some areas and stimulated starbirth in others. Even in its quiet state, a supermassive black hole's gravity can subtly steer the evolution of its galaxy. It maintains a gravitational grip on stars in the dense galactic core, helping to keep them in more ordered orbits. Without a heavy anchor at the center, some galaxies might have looser, more chaotic stellar swarms in their nuclei. In our Milky Way, for example, the central black hole, while calm now, binds a cluster of stars that orbit it like planets around an invisible sun. If that black hole weren't there, those central stars might scatter or be flung away. Instead, they circle obediently, and their orbits have allowed us to measure the black hole's mass precisely by watching their celestial choreography. The relationship between a galaxy and its central black hole appears almost symbiotic. Over billions of years, as galaxies grew through mergers and gas accretion, their black holes grew in tandem. When the black hole became too active, it would curtail the galaxy's growth by cutting off star formation. This self-regulating dance likely explains a key observation. The mass of a supermassive black hole correlates with the velocity of stars in its host galaxy's bulge and the bulge's mass. It's as though every galaxy's evolution carries the imprint of a long conversation between it and its black hole. Sometimes a friendly chat, sometimes an argument, but one that ultimately reaches an equilibrium. Consider a massive cluster of galaxies, thousands of galaxies held together by gravity. At the heart of the cluster usually lies a gigantic elliptical galaxy, itself harboring a supermassive black hole. We see giant bubbles in the hot gas that fills these clusters, blown by repeated jet outbursts from the central black hole. Those bubbles rise like hot air balloons, distributing energy throughout the cluster's core and preventing gas from cooling too quickly. In doing so, the black hole indirectly controls star formation on the scale of an entire cluster, not just a single galaxy. The effect is so pronounced that without black hole feedback, simulations of the universe predict far more stars forming in big galaxies than we observe. The black holes act as brakes on runaway starbirth. On more human timescales, a galaxy's central black hole can also be an agent of dramatic events. It can capture and shred a wayward star, causing sudden flares that outshine the entire galaxy for a time. It can influence the orbits of other black holes or dense objects, potentially sending them spiraling into the center. Over millions of years, these processes shape the nuclear star cluster and the inventory of exotic objects, like neutron stars and smaller black holes, near the core. In essence, a black hole's influence on its galaxy is like that of a heart on a body. When it beats strongly, in the active quasar phase, it sends powerful pulses that can be life-sustaining in moderation or harmful in excess. When it rests, the body is calm, but still subtly under the heart's control. Galaxies and their black holes are intertwined across cosmic time. One grows, the other responds, in a complex feedback loop. So when we gaze at a serene galaxy, glittering with billions of stars, we should remember that at its center likely resides a black hole that has, in earlier times, blown fiery winds and set the stage for how those stars came to be arranged. Black holes, though tiny relative to their expansive realms, act as cosmic conductors, ensuring galaxies do not grow without limit and that the story of star formation has both pauses and crescendos. Despite all these powerful clues and influences, for generations, black holes remained unseen directly, only inferred. They lived in equations, in the motions of stars, in bursts of radiation, but not in any image. That changed in a defining moment for science and human curiosity. Not long ago, we managed to capture an image of the unseeable. A global alliance of radio telescopes, spread from mountaintops to deserts across the Earth, worked in unison, effectively turning our entire planet into one giant eye, sharp enough to gaze across galaxies. They set their sights on a supermassive black hole in a nearby cluster of galaxies, aiming to observe the silhouette cast by its event horizon. This target was a leviathan billions of times the mass of the Sun, surrounded by a bright disk of infalling gas, an ideal candidate to reveal a black hole's visage. After years of meticulous planning, synchronization, and data analysis, the effort bore fruit. The world was presented with a haunting picture, a fuzzy, glowing ring of gold and orange with a deep, dark center. It was immediately recognizable as something extraordinary, the shadow of a black hole seen for the first time. That dark center was the imprint of the event horizon, a hole in the light where photons were missing because they had been pulled into the abyss. The ring around it was light from the accretion disk, bent and magnified by gravity into a halo. We were gazing, effectively, at the silhouette of a phenomenon that had only existed in theory until then. The image was both humbling and exhilarating. In its blur and simplicity, it confirmed decades of theoretical work. The size and shape of the black hole's shadow matched what general relativity predicted for an object of that mass at that distance. It was a direct affirmation that our understanding of gravity holds true even in nature's most extreme crucible. People around the world reacted with awe. Some described the image as witnessing the gates of hell or the eye of Sauron, grasping for metaphors to fathom the intense reality of what we saw. But beyond the drama, this was a triumph of human cooperation and ingenuity. To photograph a black hole's shadow, one must capture details as fine as seeing an orange on the moon from Earth. That required linking telescopes across continents, timing their observations to within billionths of a second, and hauling petabytes of data to be combined. It was an achievement at the very edge of what technology and teamwork could accomplish. The significance of this first image extends beyond one black hole. It opened a new window into studying these objects. We can now, in principle, see how reality behaves just outside the event horizon. By analyzing the brightness and shape of that ring, scientists can test how well our theories hold up and search for tiny deviations that might hint at new physics. The image also drives home a more philosophical point. Black holes are no longer mere abstractions. We have seen one. It is real in the most direct sense. The concept leapt from chalkboards and computer simulations into a picture we can frame and behold. In that sense, a black hole became tangible. Buoyed by this success, astronomers didn't stop at one. They turned the Earth-sized telescope network toward the quiet giant at the center of our own Milky Way. This was a tougher challenge. Our black hole is smaller, and the ring of light around it changes on timescales of minutes, as opposed to the relatively stable, hours-long patterns in the first target. After heroic efforts to freeze the flicker with algorithms and to tease out the signal from turbulent interstellar gas, they produced another image, a similar glowing ring, but this time surrounding our galaxy's very own dark heart. We now have portraits of two black holes, one a monstrous engine in a distant galaxy, one the somewhat gentler heavyweight in our backyard. They are family photos of sorts, revealing that no matter the scale, a hungry black hole paints the same telltale picture. Seeing that shadow for the first time was like finally meeting a legendary creature face to face. It was the dragon's outline emerging from the cave. And true to the best stories, it was neither a disappointment nor a monstrosity beyond comprehension. it was a bit of both in its strange beauty. The bright ring told of incredible energies and the dance of photons in curved space-time. The dark shadow spoke of the absolute darkness within, where no information escapes. With that image, humanity stepped closer to the black hole's edge than ever before, not in person, but in perception. It's a moment that will be remembered as a milestone, the day we captured a piece of a black hole's essence on camera. In the future, these images will only get sharper. We may witness movies of gas swirling, see jets at their genesis, watch as black holes feed and change in real time. But nothing will quite compare to that first glimpse, the moment the darkness of a black hole was illuminated by the light it itself sculpted. It affirmed that by persistent curiosity and ingenuity, we can reveal the universe's deepest secrets. The black hole's shadow is no longer just a calculation, it has become a sight to behold. For all the images and light black holes can produce indirectly, one of the most groundbreaking discoveries in recent times came not from seeing a black hole, but from hearing one, or rather feeling one through the fabric of space-time. In the quietness of a high-tech observatory, long tunnels with laser beams reflected back and forth suddenly sensed an almost imperceptible tremor. In that faint jitter of light was encoded an event of unfathomable violence. Two black holes, far across the universe, had collided and merged into one. When black holes spiral toward each other, they create ripples in space-time itself. Like a stone dropped in a pond sends out waves on the water's surface. These ripples are gravitational waves. As two black holes draw close, their dance quickens. They circle each other faster and faster, nearing the speed of light, and the gravitational waves they emit increase in frequency and strength. In the final moments, the two black holes crash together, merging into a single, larger black hole. This merger rings space-time like a gigantic bell, sending out a storm of gravitational waves in all directions. Then, as the disturbed new black hole settles into its final shape, the waves taper off. If one could listen to these waves by converting their frequencies into sound, it would resemble a brief chirp, a rising tone that suddenly cuts off. That chirp is the death song of two black holes becoming one. For over a century, after general relativity predicted gravitational waves, they remained elusive. They stretch and squeeze space itself, but by the time they reach us from distant events, the effect is minuscule, far smaller than an atom. Detecting them required extreme ingenuity. Finally, humans built instruments capable of measuring distance changes as small as a fraction of a proton's width. And then, one day, the signal came. The instruments recorded the characteristic chirp. We had, for the first time, directly detected gravitational waves, and they came from a binary black hole merger. The news reverberated around the world. We had heard black holes colliding. This achievement opened a new era of astronomy. No longer were we confined to using light, electromagnetic waves, to observe the cosmos. We could now use gravitational waves as well. Black holes, which are often invisible to traditional telescopes, became audible through these cosmic vibrations. In the years since that first detection, dozens of black hole mergers have been recorded. Each detection is essentially the ghostly record of a cataclysm in the distant universe, often billions of years ago, before multicellular life existed on Earth, whose faint echo is only now washing over us. Through gravitational waves, we've discovered black holes of sizes we hadn't observed before. Some were much more massive than any stellar black hole known from X-ray observations. This told us black holes can grow by merging with each other, and perhaps that some formed from stars in environments we hadn't fully envisioned. We've detected black holes spinning, and even cases where two merging black holes had spins tilted at odd angles to their orbits, causing them to wobble like tops as they merged. Subtle effects encoded in the gravitational waveform. The beauty of gravitational wave astronomy is that it gives us a way to sense the universe that is completely different from sight. It's like gaining a new sense organ. Black holes are at the forefront of this new sense, because they often merge invisibly. No light escapes them, and if they have little gas around, the merger emits no light. Without gravitational wave detectors, two black holes could collide entirely unnoticed by all our telescopes. Now we can catch them in the act routinely. Each time two black holes merge, a bit of their mass is lost, up to a few percent of the total, converted directly into gravitational wave energy. For a brief moment, the power of that event exceeds the light from all stars in the observable universe combined. Yet by the time those ripples reach us, they are so faint that it takes the most sensitive instruments ever built to detect them. The first detection was a triumph not just of technology, but of human imagination. We had imagined these black hole dances and their cosmic music, and then built the means to hear it. There's a profound emotion in knowing that the gentle rising chirp in a detector's speaker is in fact the ripple of two black holes, each perhaps 30 times the mass of the Sun, colliding a billion light years away. It connects us to an event so remote and extreme, yet through physics and engineering, it becomes almost intimate, a tiny motion in mirrors here on Earth, carrying the story of that distant tragedy. Gravitational waves have enriched our understanding of black holes. They confirmed that black holes do merge as predicted, and that such mergers are common enough to be detectable. They allowed us to test general relativity in the strongest gravitational fields. So far, the predictions hold perfectly. The waves match the theory's expectations to remarkable precision, and these waves may eventually reveal new surprises, perhaps signals from black hole neutron star collisions. Indeed, we've caught those too. Or one day, the slow in-spiral of supermassive black holes, whose long waves we might detect with pulsar timing arrays or space-based detectors. Each new type of wave is a new chapter of cosmic storytelling. For black holes, gravitational waves are like a voice, a bass vibration echoing through the cosmos. We have begun to eavesdrop on their conversations. With each detection, we expand our sensory picture of the universe, feeling more deeply the dynamic, restless activity that light alone could not reveal. It's an unfolding story of the cosmos where black holes often take center stage, not in the spotlight of brightness, but in the subtle tremors that announce the most dramatic collisions known. Black holes, for all their power and finality, harbor a subtle secret. Given enough time, they are not completely black, nor do they last forever. About half a century ago, a bold theoretical physicist blended quantum theory with the theory of black holes and arrived at a startling conclusion. The very emptiness around a black hole's event horizon isn't truly empty. According to quantum physics, even vacuum teams with fleeting particle-antiparticle pairs that pop into existence and then annihilate and disappear almost immediately. One could ask, what happens to these pairs right at the edge of a black hole? The answer that emerged was astonishing. If a pair of virtual particles forms near the event horizon, it's possible for one particle to fall into the black hole while the other escapes before they can annihilate each other. To an outside observer, that escaping particle looks as if it has been emitted by the black hole. But nothing, conventionally, escapes a black hole. So how can this be? The trick is that the black hole loses a bit of its mass energy to make it happen. The particle that falls in effectively carries negative energy from the outside perspective, subtracting from the black hole's mass, while the one that escapes carries positive energy away as radiation. The net effect is that the black hole radiates particles and light as if it were a hot object, a black body with a certain temperature. This phenomenon, now known as Hawking radiation, gives black holes a temperature inversely proportional to their mass. Small black holes are hotter and evaporate quickly. Large black holes are exceedingly cold and evaporate extremely slowly. For a stellar mass black hole, the temperature is tiny, far colder than the microwave background glow of the universe, essentially undetectable with current technology. Such a black hole would take many times the current age of the universe to evaporate significantly. making it effectively immortal on any practical timescale. But for a tiny black hole, say one with the mass of a mountain, the temperature would be higher, though still very low by everyday standards. As the black hole radiates, it loses mass, and as it loses mass, it gets hotter and radiates faster. This leads to a runaway crescendo at the end of a black hole's life. In its final moments, if it ever becomes very small, it would radiate furiously, heating up to billions of degrees and likely exploding in a burst of high-energy particles and gamma rays. No such final burst has ever been observed, which isn't surprising. If primordial black holes of small size were common, we might have seen one by now as a mysterious explosion in the sky. Their absence tells us that if primordial black holes exist at all, they're either large enough to still be around, or they were never abundant. Still, the insight that black holes evaporate was profound because it married quantum mechanics with gravity in a tangible way. It showed that black holes are not one-way traps in the absolute sense. They can very slowly leak energy, and presumably information, back out into the universe. They obey a version of the second law of thermodynamics. They have entropy, proportional to the area of their event horizon, and a temperature, and they will eventually come to thermal equilibrium with the rest of the universe by radiating away. The idea that black holes evaporate forces a change in perspective. These cosmic abysses are not eternal. Given enough eons, even the mightiest black hole will shrink and ultimately vanish in a final flash. In a universe far, far into the future, long after the stars have burned out and galaxies have dispersed, one can imagine the last black holes sizzling away into a faint glow, like embers in the darkness, until they wink out. It is a melancholy yet beautiful vision of an ultimate heat death. Even the darkness itself evaporates. For present-day astrophysical black holes, Hawking radiation has no noticeable effect. A black hole continuously feasting on surrounding gas or merging with others grows far faster than it could ever evaporate. In fact, the faint trickle of Hawking radiation is overwhelmed by the bath of cosmic microwave background radiation still filling the universe. Paradoxically, the universe's residual light feeds energy into a black hole faster than the hole loses it. Evaporation becomes important only for hypothetical, isolated small black holes. But the theoretical importance of Hawking's discovery is immense. It provides a crucial link between three pillars of physics: quantum theory, general relativity, and thermodynamics. In the gentle hiss of Hawking radiation, we see a hint of how these frameworks unify. The notion that the event horizon's area corresponds to entropy, and that black holes have a finite temperature was shocking at first, but it has become a cornerstone of modern theoretical physics. Hawking radiation also set the stage for one of the deepest puzzles in physics: the information paradox. If a black hole eventually evaporates completely, what happens to all the information about the things that fell into it? Is it encoded somehow in the Hawking radiation, or is it truly lost to the universe? This question challenges our understanding of how quantum mechanics works on cosmic scales. But regardless of that puzzle, which we will delve into next, Hawking's discovery transformed black holes from deadly, unchanging endpoints into dynamic objects with life cycles of their own. They can be born, they can grow, and yes, they can slowly die. It's poetic in a way. An entity that swallows everything can, in the end, give back to the void. A black hole evaporating is like a drop of ink spreading out into a vast ocean. The concentrated darkness dilutes into faint radiation, returning its energy to the wider universe. No one has witnessed this process directly, and perhaps no one ever will, given the immense timescales. But the equations speak, and they tell us that even black holes whisper ever so softly and fade away when left alone. Here, we confront perhaps the most confounding riddle posed by black holes. It arises from the clash of two deep principles: the absolute gravity of a black hole and the inviolable laws of quantum physics. We've learned that black holes can evaporate over time via Hawking radiation. That radiation, as originally calculated, appears to carry no information about what fell into the black hole. It's featureless, like heat from a furnace. But quantum mechanics has a stringent rule. Information cannot be destroyed. If you know the exact quantum state of a system, it will evolve into another exact state. In principle, you can always reverse the process and recover the initial information. Burning a book, for example, scrambles the information into ash and smoke. But in theory, ignoring practical limitations, that information is still present in the arrangement of particles and could be reconstructed. A black hole, however, seems to take in a book and later evaporate without a trace of what was written in it. The information, by all accounts, would be gone. This is the black hole information paradox. When it was first suggested that a black hole's evaporation would destroy information, it shook the physics community. It wasn't just about black holes. It struck at the heart of what quantum physics means. If black holes can truly erase information in a way that nothing else we know of can, then our understanding of physics at a fundamental level is incomplete or wrong. Either quantum mechanics, which has never failed a laboratory test, would need revision, or our picture of black hole evaporation was missing key details. The paradox can be summed up in a stark scenario. Throw an encyclopedia into a black hole. From the outside, you can no longer read it. The information in those pages is effectively lost to the observable universe. Over a fantastically long time, suppose the black hole evaporates completely into featureless Hawking radiation, like a final puff of steam. Now, where is the information that was in that encyclopedia? Quantum theory insists it must still be in the outgoing radiation somehow, perhaps encoded in subtle correlations between particles. But Hawking's original calculation implied it was not. It was simply lost. This contradiction has led to decades of intense thought and debate. Many ideas have been proposed to resolve the paradox. Some suggested that perhaps black holes don't evaporate entirely. Maybe they leave behind some kind of stable remnant that stores the information, though that concept raises other issues. Others considered that when black holes evaporate, they might spawn a baby universe that carries away the missing information, sequestered from our own universe. A leading perspective today comes from the holographic principle, which posits that all the information that falls into a black hole is not lost, but is somehow stored on the event horizon's surface, like a cosmic ledger or hard drive with an enormous capacity measured in bits per area. In this view, as the black hole evaporates, the information slowly gets encoded in the Hawking radiation in highly scrambled form, so scrambled that Hawking's original calculation, which treated the radiation as perfectly random, missed the subtle way information could leak out. In recent years, theoretical breakthroughs using ideas from quantum information theory and holography have given tantalizing evidence that information does indeed escape in the Hawking radiation, albeit in an extremely encrypted form. It appears that the radiation is not perfectly featureless after all. Tiny deviations from a perfect thermal spectrum carry away the hidden message of what fell in. As the black hole shrinks, these correlations become significant and ensure that by the end of evaporation, no information is truly lost. However, exactly how this happens requires physics beyond what we currently fully grasp, essentially a true theory of quantum gravity. One provocative proposal was the idea of firewalls. Some researchers speculated that perhaps the interior of an old black hole, one that has evaporated down to a small size, might not be the smooth continuation of space that general relativity predicts. Instead, a searing wall of high-energy quanta at the horizon could incinerate anything trying to enter or exit, which might enforce information conservation at the expense of something called the equivalence principle, the idea that falling through a horizon should feel uneventful. This idea is controversial because it essentially says that the event horizon might become a violent place in certain conditions, contradicting the classical notion that crossing a big black hole's horizon is uneventful. The very fact that serious scientists would entertain such an outlandish concept shows how pressing the information paradox is. It seems some cherished principle of physics must give way, and they are debating which one. Amid these debates, a common sentiment has emerged. The information paradox is not just a puzzle about black holes, it's a beacon pointing toward a deeper understanding of nature. To fully resolve it, we likely need a successful theory of quantum gravity, a framework that unifies general relativity, our theory of the cosmos, with quantum mechanics, our theory of the microscopic. In chasing the paradox, physicists have developed new ideas, like holography and quantum entanglement arguments, that have already yielded partial insights. Most physicists now suspect that when we finally have a full theory of quantum gravity, be it an evolved form of string theory, loop quantum gravity, or something else, the paradox will dissolve, and we will see that no information was truly lost to begin with. From a philosophical standpoint, the information paradox forces us to consider what identity means in a physical sense. If a person falls into a black hole, is the information that constituted their being, every particle, every quantum state of their body, preserved in principle, or is it irretrievably destroyed? It's a mind-bending contemplation. Nature seems to guard information as a fundamental currency, yet a black hole seems to be a supreme destroyer of it. Resolving that contradiction may tell us whether the universe is ultimately deterministic and information-preserving, or whether there are places, like black holes, where the usual rules falter in a profound way. As of now, the consensus among theorists leans toward information being preserved. Black holes probably do not violate the laws of quantum mechanics at the fundamental level. Instead, they challenge us to better understand those laws under extreme conditions. The paradox has been a driving force behind some of the most creative theoretical work of the last half-century. Slowly, like a code being deciphered, pieces are falling into place. Entropy corresponding to horizon area, radiation carrying information in subtle ways, horizons having microstates. All hint that black holes are puzzles meant to be solved, and in doing so, we learn the language of a deeper reality. The information paradox stands as both a warning and an inspiration. A warning that something in our knowledge is incomplete, and an inspiration that by completing it, we will grasp a more profound truth about how the universe works. Black holes are more than just astrophysical objects. They are theoretical laboratories for the frontier of physics. At the meeting point of extreme gravity, quantum effects, and thermodynamics, black holes present a crossroads where our current theories collide and intertwine. We've already seen hints of this, the notion that black holes have entropy and temperature, thermodynamics, that they evaporate via quantum processes, and that their existence is predicted by general relativity. In a sense, a black hole is where the cosmic, the very large, meets the quantum, the very small, and understanding them fully requires a theory that can handle both, a theory of quantum gravity. The laws of black hole mechanics, formulated in the early 1970s, bore an uncanny resemblance to the ordinary laws of thermodynamics. They stated, for example, that the area of a black hole's event horizon never decreases, analogous to entropy disorder, never decreasing in a closed system, and that there is a quantity, surface gravity, analogous to temperature. Initially, these parallels were thought to be just analogies. But Hawking's discovery that black holes radiate gave literal meaning to them. Black hole entropy is real and enormous. A black hole of a few solar masses has vastly more entropy than the Sun, and black hole temperature is real, though tiny for large holes. This realization was a beacon illuminating a deeper truth. Gravity, quantum mechanics, and thermodynamics are intimately connected. It's as if three very different languages, the language of curved space-time, the language of particles and probabilities, and the language of heat and energy, all converge in describing a black hole. To speak fully about a black hole, one has to be multilingual in physics. This is both inspiring and daunting. It suggests that our current separation of physics into different domains, quantum versus cosmic, for instance, is artificial. There is a unity to be found. Many physicists believe that to resolve the information paradox and truly understand the singularity at a black hole's core, we need a workable quantum theory of gravity. Various approaches are being explored. String theory, for example, posits that fundamental entities are tiny vibrating strings, and that black holes might be composed of very tightly wound strings or brains. In some string theory calculations, scientists can account for the entropy of certain black holes by counting the quantum states of those strings, and the result exactly matches the Bekenstein-Hawking entropy, the formula relating entropy to horizon area. This was a triumph, indicating that a quantum gravity theory can, in principle, explain black hole thermodynamics. It's as if string theory peeked behind the event horizon and saw all the microscopic degrees of freedom that make up a black hole's enormous entropy. Another concept that has emerged is the holographic principle, which we've touched on. It suggests that everything that happens inside a volume of space, like the interior of a black hole or even our observable universe, could be described by information encoded on the boundary of that volume, like the event horizon surface. In a holographic description, the three-dimensional interior is projected from data on a two-dimensional surface, similar to how a hologram encodes a 3D image on a flat film. Remarkably, a prime example of this principle is a result from string theory called the ADS-CFT correspondence. In that scenario, a gravitational world in a certain kind of space with an extra dimension is exactly equivalent to a quantum field theory without gravity on its boundary. In such a duality, a black hole in the interior corresponds to a hot thermal state in the boundary theory. The information paradox in the gravitational picture becomes a much more tractable question in the boundary picture, where there is no paradox because standard quantum theory applies. This duality has provided strong evidence that black holes, when viewed with the right theoretical lens, do not truly destroy information. The information is encoded in subtle ways, consistent with quantum mechanics, just not in ways we find obvious from our usual perspective. Beyond string theory, other approaches like loop quantum gravity attempt to quantize space-time itself, suggesting that space may be made of tiny, discrete units. In some loop quantum gravity models, the black hole singularity might be avoided. Instead of a point of infinite density, you get a bounce, where space-time curves enormously, but then rebounding occurs, potentially connecting to a new region of space or another universe. If so, perhaps the interior of a black hole could connect to somewhere else through this quantum bridge, effectively making something like a wormhole or a white hole as the other side of the black hole. These ideas are speculative, but they share a theme. Quantum effects likely save us from the infinities and paradoxes that classical general relativity predicts. Black hole thermodynamics teaches us that a black hole's event horizon behaves like something with microscopic structure. It can store information and has a kind of granular nature when viewed through the lens of quantum theory. This hints that space-time itself has a microscopic, quantum structure. Much as a smooth steel ball is actually a lattice of atoms if you look closely, the surface of a black hole might be composed of tiny quantum bits of area. That would explain why the entropy, number of bits of information, scales with area, not volume. The information content is on the surface. All these insights are arrows pointing toward a future theory. We do not have that theory complete yet, but black holes have been generous with clues. By studying them, theorists discovered deep links between gravity and thermodynamics, formulated conjectures about the holographic nature of the universe, and tested ideas of quantum gravity in thought experiments and simplified models. In a way, black holes are to theoretical physics what the Rosetta Stone was to archaeology, a cipher through which a new language, quantum gravity, can be decoded. They push our understanding to the breaking point, forcing us to invent new concepts to describe what happens under such extreme conditions. One day, if a full theory of quantum gravity is achieved, black holes will likely be central in its narrative. In that theory, black holes will no longer have singularities in the sense of infinities. Something will replace that pit of endless density, perhaps a churning quantum foam, a tangle of space-time filaments, a doorway to another domain, or something we haven't yet conceived. And that theory will elegantly show how information, gravity, and quantum behavior reconcile. Until then, black holes remain our greatest teachers in the quest for unity in physics, hinting at the grandeur of a universe where all forces and particles dance to a single tune we have yet to fully hear. Black holes also capture our imagination, not only for what we know about them, but for the tantalizing possibilities they suggest. Could a black hole be a door to somewhere else? What lies beyond the confines of the event horizon? Is it just oblivion, or might it connect to something unexpected? These questions straddle the boundary between science and philosophy, between rigorous theory and speculation. One concept that arises from the mathematics of general relativity is the white hole. If a black hole is a region where nothing can escape, a white hole is the opposite, a region where nothing can enter, from which matter and light can only emerge. In effect, it's the time reversal of a black hole. If you take the equations for gravitational collapse and imagine running time backward, you get a white hole. Such an object would constantly spew out anything that ever fell into its black hole counterpart in the past. It would be like a cosmic fountain, an out-only region of space-time. While intriguing in theory, white holes have never been observed, and most physicists doubt they actually exist in our universe. They appear to be unstable. Any disturbance would turn a white hole into a black hole. Some have whimsically wondered whether the Big Bang itself, which spewed matter out of a singular point, was a kind of white hole. But that idea is more poetic analogy than testable theory. For now, white holes remain a mathematical curiosity, a reflection of black holes in the mirror of time, with no evidence that nature ever chose to make one. Even more captivating is the idea of wormholes, tunnels through space-time that could connect distant parts of the universe, or perhaps different universes entirely. This concept originally arises when one studies the geometry of a non-rotating black hole. Mathematically, the complete extension of such a solution hints at a bridge connecting two regions of space-time. This bridge was dubbed a wormhole, or more specifically, an Einstein-Rosen bridge. However, that particular wormhole is not traversable. It pinches off too quickly for anything, even light, to pass from one end to the other. It's like a tunnel that collapses before you can get through. But it planted the seed of an idea, perhaps under the right conditions, say, with a rotating black hole, or with the addition of exotic forms of matter. A stable, traversable wormhole might exist. A traversable wormhole would essentially be a cosmic shortcut or portal. You enter one mouth of the wormhole and emerge from the other mouth at a distant location or a different time. It's the stuff of countless science fiction stories, a convenient tunnel through space and time. Physicists have explored the wormhole concept with equations. The consensus is that if wormholes are possible at all, they likely require exotic matter with negative energy density to hold them open. Otherwise, the tunnel collapses into a black hole, white hole pair. We don't know of any way for such negative energy matter to accumulate naturally, though quantum effects can create small regions of negative energy. So traversable wormholes remain hypothetical. If one did exist, a traveler falling into one end wouldn't hit a singularity. Instead, they'd feel gravity's pull and some extreme tidal forces, then, in theory, emerge in a completely different region of space-time. The journey might be short, even though the separation in normal space could be immense. No evidence for any kind of wormhole has been found in the universe. We have not seen stars disappearing in one location and appearing elsewhere, or strange lensing effects that would indicate a shortcut in space-time. But intriguingly, modern physics, especially in certain speculative quantum gravity theories, often finds wormholes cropping up in math, sometimes tiny ones at the Planck scale, forming a space-time foam, or connections between black holes and entangled particles, as in the thought-provoking ER-EPR conjecture, which suggests a link between wormholes and quantum entanglement. It may turn out that wormholes exist, but are either microscopic or effectively inaccessible, or they may not exist at all, and nature may enforce cosmic censorship that prevents such causal shortcuts. Then there is the idea of extra dimensions. Some theories, notably string theory, suggest that our universe might have more spatial dimensions than the three we directly experience. These extra dimensions could be curled up at small scales, or we could be confined to a three-dimensional brain within a higher dimensional space. If extra dimensions exist, black holes could potentially take advantage of them. For instance, in certain models with large extra dimensions, a black hole could leak gravity into those dimensions and evaporate faster, or high-energy collisions, like those in particle accelerators or cosmic rays, might produce microscopic black holes. There was even a brief flurry of public concern before the Large Hadron Collider turned on, when people wondered if it could produce a black hole that would swallow the Earth. Physicists responded that if the collider could make tiny black holes, which was considered possible in some speculative models, those black holes would evaporate almost instantaneously via Hawking radiation. Indeed, no such micro-black holes have been observed at the LHC, putting limits on those theories of extra dimensions. Extra dimensions also allow for exotic objects, like black strings or black rings in higher dimensional gravity. But those are beyond what we could detect in our 4D space-time shadow of the full reality, if such reality exists. Some have speculated that perhaps what we see as a black hole is only part of a higher dimensional object, like the 3D cross-section of a 4D black hole, analogous to how a 3D object passing through a 2D plane appears as a changing 2D shape. It's a wild idea, but it underscores that black holes force us to think outside the familiar. In the realm of speculation, one can imagine fantastical scenarios, falling into a black hole and popping out of a white hole in another universe, or black holes being gateways to time travel, since moving through a wormhole could in principle allow backwards time steps under relativity. These remain squarely in the hypothetical. Our current understanding says that if you jump into a black hole, you will be shredded by tidal forces and then crushed at the singularity, not transported to a wonderland or mirror universe. Every physically reasonable analysis suggests that a trip into a known black hole is a one-way ticket to destruction. Still, the fact that our theories allow such curious solutions at all, white holes, wormholes, higher dimensional holes, is food for thought. They haven't been realized, as far as we know, in our universe, but they tell us the space of possibilities is vast when dealing with gravity and quantum law at extremes. The speculative frontiers remind us that black holes sit at extremes where our knowledge frays. Could a black hole ever turn into a white hole, spewing everything back out in a final cosmic act? Could two black holes be connected back to back as an intergalactic subway tunnel? We find no evidence for these outcomes, but considering them stretches our thinking. In the end, whether these exotic ideas hold any truth or are just mathematical quirks, exploring them deepens our appreciation for how strange the universe might be and how much more we have to learn. Black holes push us to ask, what if, at the grandest scales? And that question is the seed of discovery. Few phenomena illustrate the relativity of time and space better than a black hole. What a black hole does to time is as dramatic as what it does to light. To understand this, consider three vantage points. 1. An intrepid, and perhaps doomed, astronaut falling into a black hole. 2. A distant observer watching that fall from afar. And 3. A spacecraft trying to orbit close to the black hole without crossing the horizon. For the person who falls in, the journey is surreal, but not in the way one might expect. If the black hole is huge, say, the one at the center of a galaxy, our falling astronaut might not feel anything particularly special at the event horizon itself. No dramatic jolt or sudden change. There's no signpost in space saying, "You are now entering the black hole." To the falling astronaut, space still looks black in all directions, and local physics still behaves normally, aside from the intense gravity. However, as they continue inward, gravity's tidal forces grow inexorably. If it's a smaller black hole, these forces become lethal well before the horizon, stretching the astronaut into a thin strand of matter long before they reach the horizon. But in a supermassive black hole, they might actually cross the horizon intact, and only later, much deeper in, feel those catastrophic tides. No matter what, once inside the horizon, all paths lead down to the center. Our falling astronaut cannot avoid the singularity. Moving forward in time means moving closer to the singularity at the core. From the astronaut's own perspective, they reach the singularity in a finite amount of time. Their clock ticks along normally. Perhaps they have only hours or minutes from crossing the horizon until they meet the central doom, depending on the black hole's size. Now consider the distant observer, watching through a telescope as their friend plunges toward the black hole. To this observer, the story looks very different. As the astronaut approaches the event horizon, the distant watcher sees their motions slow down, as if someone hit a cosmic slow-motion button. The astronaut's clocks appear to tick ever more sluggishly. If the astronaut waves or flashes a light in a regular rhythm, those signals come out stretched in time. The light from them shifts to redder and redder wavelengths, a gravitational redshift, quickly fading out of visible sight into infrared, then radio, then silence. In fact, the distant observer never truly sees the astronaut cross the event horizon. Instead, the astronaut appears to approach it ever more asymptotically, slowing to a crawl and growing dimmer, their image eventually smearing into a faint red ember and then vanishing. To the outside world, the astronaut becomes essentially frozen on the edge of the black hole, taking an infinite time, from their perspective, to actually fall in. Of course, in reality the astronaut does fall in and meets their end, but no information from that tragic fate can reach the outside. So from the external view, the fall looks never-ending and incomplete. The astronaut's image is stuck on the threshold. This discrepancy isn't a contradiction. It's a manifestation of how time and light behave near a black hole. Time itself flows at different rates in different places when gravity is strong. At the event horizon, outgoing light is so redshifted and delayed that to an outsider, it effectively never emerges. Meanwhile, for the infaller, their own time is perfectly normal as they experience it. Relativity allows each perspective its own reality, and only a synthesis of them gives the full picture. Now imagine a third scenario. An observer who doesn't fall in but tries to orbit or hover close to the black hole's horizon without crossing it. This observer will experience time in an unusual way as well. Their time runs slower relative to someone far away in weaker gravity. Suppose they orbit precariously close to the horizon for what they measure as an hour, and then return to a safe distance. They might find that many hours, or days, or years, depending on how close and how fast, have passed in the rest of the universe during their excursion. They have essentially traveled to the future. This is a genuine effect of time dilation near a black hole, also seen, to a far lesser extent, near any massive body like Earth. In principle, a sufficiently advanced civilization could use this effect for time travel to the future, go park near a supermassive black hole for a while, then come back to find civilization much further along. It's the scenario famously illustrated in science fiction, such as the movie Interstellar, where minutes near a black hole equated to years back on Earth. Orbiting near a black hole also gives a front row seat to some optical oddities. Light from the rest of the universe doesn't follow straight paths near a black hole. It curves and swirls. An observer close to the horizon might see the entire sky above warped into a small, bright ring as light from all around gets bent into their view. They might even catch a glimpse of the back of their own head, theoretically, because light can orbit the black hole too. There is a particular orbit called the photon sphere, about 1.5 times the horizon radius for a non-rotating black hole, where light can circle the hole. An object behind the black hole relative to you might have its image loop around and appear in front of you, perhaps multiple times, each fainter and more distorted than the last. The visual distortions would be extreme, as if space itself were a hall of mirrors. This interplay of perspectives around a black hole is not just a trick of viewpoints. It's a profound demonstration that space and time are fluid, dynamic, and relative. To the person falling in, crossing the horizon is uneventful, but their end comes quickly. To the outside person, the fall never completes, and the infaller fades away. To someone orbiting nearby, time slows, and the outside universe's clocks speed up, and the view warps fantastically. All these narratives are true in their own frames of reference. What does it mean, philosophically, that time can stretch and skew so much? Black holes force us to abandon the notion of a universal, absolute time. Each vantage has its own time, and gravity weaves them into a tapestry where no single thread is privileged. It's a reminder that our intuitions, born of everyday experiences, are woefully inadequate for cosmic extremes. If one were writing a story of a fall into a black hole, it would be a tragedy from the hero's viewpoint, an eternal suspense from the audience's, and a bizarre odyssey from a nearby companion's, and all would be correct. Ultimately, whether you watch from afar or take the plunge yourself, black holes underscore the relativity in relativity. They stretch our understanding of time and causality, proving it can be as pliable as taffy under the right conditions. They give us scenarios where two seemingly opposite statements, the astronaut fell in and died in seconds, versus the astronaut never fell in, even after eons, are both true in their own contexts. The reconciliation lies in the mathematics of space-time, but described in plain language, it remains one of the strangest features of our universe. Not all black holes sit majestically at galaxy cores or announce themselves by tearing stars apart. Some are drifters, wandering the cosmos unseen. These are the rogue black holes, solitary, star-sized black holes that have been flung free of their birthplaces or left isolated in interstellar space. They roam the galaxy like invisible phantoms. How does a black hole go rogue? One way is through gravitational slingshot events. In the chaos of a dense star cluster or a galaxy's core, interactions can kick a black hole out of its nest. If a black hole was once in a binary system and its companion star went supernova, the explosive kick could send the new black hole hurtling away. Or if two galaxies merge and their central black holes coalesce, the newly merged black hole can receive a recoil, a kind of gravitational kick, from the asymmetric blast of gravitational waves, potentially ejecting it from the galactic center. There are also scenarios where multiple black holes in a cluster have close encounters that fling one of them outward at high speed. Over cosmic time, these processes have likely populated our Milky Way with wandering black holes. These nomads are virtually invisible. A black hole without a companion or accretion disk emits no light. It's as dark as a chunk of pure night, gliding through space. To detect a rogue black hole, we must rely on its gravitational effects. One telltale sign is microlensing. If a black hole passes in front of a distant star from our viewpoint, its gravity can bend and magnify the star's light. We would see the star momentarily brighten or shift in position, even though no object is visible. By carefully monitoring millions of stars in the galaxy, astronomers have caught a few such events, and some are best explained by free-floating black holes. Indeed, astronomers recently found strong evidence for an isolated black hole roughly 5,000 light-years away. Over the course of months, a background star's apparent position and brightness were distorted in a way that indicated a compact object of about 7 solar masses passing in front of it, likely a lone black hole. That dark traveler, a remnant of a long-ago supernova, drifts through the Milky Way's spiral arms, unaccompanied by any star, effectively a ghost. And our galaxy may harbor millions more like it. For every massive star that died and didn't get kicked into a tight binary, a lone black hole could be roaming. Could one pose a danger to us? The idea is a staple of science fiction horror, an invisible destroyer moving silently through space. In reality, space is enormously vast, and even millions of rogue black holes are spread thin. The odds of one coming close enough to our solar system to disrupt planetary orbits are exceedingly remote. But the concept is chilling nonetheless. A rogue black hole could drift just a light year away, and we might barely notice, except that some stars would wobble oddly, or lensing events would spike in its vicinity. These solitary black holes likely have subtle effects. As they wander, if one passes through a nebula or molecular cloud, it might capture a bit of gas, creating a brief accretion disk and a flash of X-rays, a momentary flare betraying its passage. If one eventually slows down through dynamical friction and settles in a galaxy's halo, it might one day encounter a star and capture it, becoming visible as an X-ray binary after eons of solitude. We haven't observed such a transformation yet, but it's within the realm of possibility. In a poetic sense, rogue black holes are cosmic Ronin, masterless, traveling from one gravitational domain to another. Once the core of a bright star or a member of a binary partnership, now they are alone, carrying the mass of a sun in a package the size of a city, with only their gravitational pull as a calling card. They remind us that the universe has dark wanderers and lost souls, not just the organized systems we easily see. When we gaze up at the night sky, we might imagine that among the glittering stars and nebula, there are also these dark interlopers moving silently. They add a layer of mystery to the galaxy, unseen mass in motion. Only through careful observation, catching the slight bending of starlight or detecting the faint tug on a star's motion, can we even infer they are there. The vast majority will likely remain unknown to us, blending into the darkness. The era of routinely observing rogue black holes may still be far off, but simply knowing they wander out there expands our sense of the cosmic wild. It reminds us that for everything we see, there is much we don't see, and sometimes the most powerful things announce themselves only by their absence or by a whisper of gravity. The Milky Way becomes a more intriguing place, populated not just by stars and luminous phenomena, but also by these dark, drifting punctures in space-time. They are the quiet counterparts to the roaring quasars and X-ray binaries, a silent population of the fallen. Black holes have been part of the universe's story from the early chapters. They are not just endpoints of the stellar life cycle today. They were present in the cosmos's youth and have helped shape cosmic history. In fact, one of the great challenges in modern astrophysics is explaining how supermassive black holes managed to form so quickly in the early universe. Not long after the Big Bang, before even 1 billion years had passed, we see evidence of quasars, incredibly bright galactic centers powered by black holes of billions of solar masses. For such a black hole to exist so early, it must have grown very fast or started from a very large seed. The first stars, the so-called population 3 stars, formed perhaps 100 to 200 million years after the Big Bang. These stars were likely very massive, hundreds of solar masses, due to the pristine, metal-free gas conditions, and when they died, some would have left black holes, maybe tens of solar masses. These were the universe's first black holes, the embers of the first stars lighting up the cosmic dawn. If one of those early black holes found itself in a dense region, like the center of a small protogalaxy, it could feed on gas and merge with its neighbors, growing larger over time. Still, going from, say, a 50 solar mass seed to a billion solar mass quasar in a few 100 million years is no small feat. Some mechanisms might have helped. Perhaps some of those first stars were so massive, imagine a single star of 100,000 solar masses, that they collapsed directly into a black hole of, say, 10,000 solar masses, skipping the step of supernova and neutron star entirely. Such a direct collapse black hole would give a huge head start. We call these hypothetical giants direct collapse black holes, or quasi-star remnants. The idea is that in the early proto-galaxies, if cooling was inefficient, due to lack of elements like carbon or oxygen that aid fragmentation, a huge cloud could contract without breaking into many stars, forming one megastar or an unstable disk that funnels mass into a central black hole seed. Another assist could have come from galaxy mergers. The early universe was smaller and more dense. Proto-galaxies collided frequently. If each had a black hole seed, those holes could sink to the center of the new, merged galaxy and eventually merge with each other. Each merger could produce a bigger black hole and potentially a kick, though if the galaxy is massive enough, the black hole may remain bound. Also, the tumult of mergers would drive lots of gas toward galactic centers, providing a feast to fuel rapid growth, a phase we might identify as a bright quasar. So a combination of moderately large starting seeds and frenzied early feeding could yield a billion solar mass black hole by the time the universe is, say, 700 million years old, which is what we observe. Primordial black holes, as previously discussed, are another candidate for seeds. If any relatively large ones formed in the Big Bang's aftermath, they could start growing even before the first stars. But the evidence for primordial black holes as a significant population is not there at the moment. It remains a theoretical possibility. What we do know is that by the time the universe was 1 billion years old, it already had black holes that qualify as monsters by today's standards. These early black holes likely had a profound impact. They would have been pouring out radiation and perhaps launching prodigious jets, affecting their host galaxies and maybe even the intergalactic medium around them. The epoch of ionization, when the universe's hydrogen was ionized by the first light sources, might have contributions from quasars, not just young stars. Those early black holes were not quiet spectators. They were actors on the stage, possibly shutting off star formation in their host galaxies, even as those galaxies were still young. As time went on, the universe expanded and evolved. The rate of galaxy mergers slowed. Star formation settled into a slower pace in many galaxies. The supermassive black holes that had grown so rapidly early on then often calmed down, having consumed most of the nearby fuel. Our Milky Way's black hole, for instance, is relatively starved now and only occasionally snacks on a passing gas cloud. But we see its active past indirectly, in the massive bubbles of gamma ray emitting gas blown above and below the galactic center, likely a sign of an energetic phase millions of years ago. Understanding how black holes formed in the early universe helps complete the picture of cosmic history. The first black holes were both products and agents of cosmic evolution, products of collapsing matter in a young universe, and agents that influenced the formation of galaxies and stars around them. When we look at the farthest quasars, we are peering into a time when the universe was in its teenage years, full of energy and growth spurts, with black holes growing like weeds. In a sense, the evolution of the universe and the growth of black holes have been entwined threads from the very beginning. Today, billions of years later, the universe has many matured galaxies with central black holes that grew in that earlier frenzy and then went quiet. Those black holes serve as archaeological evidence of that formative epoch. They are giant scars of the early universe's creativity and violence, much as mountains and craters tell us about Earth's geological past. By studying the distribution and masses of black holes in distant quasars versus those in local dormant galaxies, we glean insights into that long-ago time. So black holes teach us not only about gravity and quantum mysteries, but also about our cosmic origins. They have been there since the first stars died, and perhaps even earlier. They are the storytellers of the universe's youth, holding in their existence the tale of how gas clouds became galaxies and how tiny instabilities grew into mighty structures. Each massive black hole in a distant quasar is like a messenger from that dawn, saying, "I was here, shining brightly when the universe was young." Through them, we study not just black holes themselves, but the dawn of structure and the rise of cosmic order out of chaos. In confronting black holes, we find ourselves confronting the very limits of understanding and reflecting on deep questions about identity, destruction, and the fate of information. Black holes are often seen as the universe's ultimate agents of annihilation. They swallow light, time, and anything else that crosses their threshold, seemingly erasing all traces of those objects from our universe. In that sense, a black hole is a kind of cosmic death, the death of a star, the death of information, the end of a path. Standing before a black hole's event horizon, one can't help but draw parallels to concepts of an ultimate point of no return. Yet, what black holes have taught physics is that endings may not be as absolute as they appear. The paradox of information, whether information that falls into a black hole is lost forever, forces us to reconsider our notion of destruction. Quantum theory tells us that information is never truly destroyed, even if it is hopelessly scrambled. So if even a black hole ultimately cannot obliterate information without a trace, as many physicists now suspect, then perhaps nothing is ever completely lost. This is a profound and somewhat comforting thought, that the essence of things, the information that defines them, has a way of enduring, even in the maw of a black hole. Think about the no-hair idea. Two very different stars, one a blue supergiant and one a red giant, could collapse into black holes of the same mass and spin, and then be indistinguishable from the outside. The individuality of the stars, their hair, is gone. The black hole does not reveal what it has consumed. This sounds like obliteration of identity, and classically it is. But if the modern view is correct, the information isn't truly destroyed. It's just hidden in correlations in the Hawking radiation or imprinted somehow on the horizon. In a poetic sense, one could think of it as reincarnation in code. The pattern that was a star is diffused into the universe at large over eons, via subtle encodings in radiation. No one could practically reconstruct it, but it's not utterly erased from existence. Black holes also resonate with the concept of death and rebirth in another way. The death of a star gives birth to a black hole. The chaos a black hole causes can lead to new stars forming as jets compress gas or as mergers shake galaxies. In a long time frame, a black hole might evaporate and return its mass energy to the universe, in essence, completing a cycle. This parallels natural cycles we see elsewhere, say, a forest fire that destroys yet returns nutrients to the soil from which new life springs. It's as if black holes are part of a grand cosmic recycling program, albeit on scales of time and energy far beyond everyday comprehension. Moreover, black holes force humility about knowledge. The interior of a black hole is fundamentally unknowable to an outside observer. It's cut off causally from the rest of the universe. This is a bit like our own mortality. Whatever lies beyond the horizon of death is not accessible to the living. Black holes give that abstract idea a concrete form, a region from which no information can reach us. In that way, they are like a physical embodiment of mystery. One stands on the outside and wonders, but cannot see inside. It's a reminder that there may always be horizons beyond which our empirical knowledge breaks down. Yet, rather than simply signifying despair or the futility of effort, black holes have inspired humans to unprecedented feats of discovery. We did not throw up our hands at the sight of an information horizon. We built theories and experiments to get as close to it as possible. We figured out how to image an event horizon's shadow and how to detect the ripples from events beyond a horizon. In a sense, we've learned to navigate around the edges of the unknown and glean truths without directly peering inside. There's something uplifting in that. It suggests that even if some things are fundamentally inaccessible, we can still learn about them indirectly and push the veil a little further back. Black holes also bring forth existential metaphors. The idea of an event horizon can be seen as analogous to moments in life beyond which things are forever changed, a point of no return. Dropping past a black hole's horizon is a one-way journey, much like certain decisions or events in life, or the act of death, are one-way. The philosophical question arises, is there anything beyond that one-way journey? In black hole physics, if information is preserved, then in some form, nothing is truly lost beyond the horizon, even if it's not recoverable in practice. If one extends that metaphor, it might suggest a kind of natural optimism, that traces remain, that effects endure, that no influence vanishes utterly. These musings blend science with philosophy, and even a touch of spirituality. Of course, a black hole isn't literally making statements about human life or meaning, but it provides a rich canvas on which to project such thoughts and to test our intuitions. It invites reflection on how the universe handles extremes. In the end, black holes teach us a kind of cosmic perspective. They are extreme and violent, yet from them we have learned some of the most gentle and profound truths about the universe's order, like the unity of physical laws. They are terrifying in concept, yet we pursued them and found awe rather than doom. There is a famous saying, "If you gaze long into an abyss, the abyss also gazes into you." In a way, when we literally gazed into the abyss, the black hole, M87, what gazed back was our own collective achievement, the ring of light that said, "You did it. You saw me." The abyss reflected our curiosity and ingenuity. Black holes confront us with the reality that the universe is not made for us. It has places utterly inhospitable and bewildering. But by studying them, we've turned these cosmic abysses into sources of knowledge and even inspiration. They forced us to extend physics, to invent new mathematics, to contemplate the destiny of information and the nature of time. They underscore themes of impermanence and persistence. Stars die, but something of them becomes a black hole. Black holes evaporate, but something of them returns to the universe. Perhaps above all, black holes remind us of our own drive to understand. Faced with what looked like a literal hole in the universe, a place where all light and certainty vanish, we didn't recoil permanently. We reasoned, we theorized, we built instruments, and we revealed a bit of the hole's secret. In doing so, we confronted fears about the unknown and made them manageable, even beautiful. The emotional journey from fearing the black hole, once a term of dread or at least skepticism, to photographing it and listening to its waves is a testament to human curiosity. Standing at the edge of a black hole, literally or figuratively, we are looking into forever, into a place where our rules break down. It's a vantage that makes one feel small, but it's also a vantage that highlights the grandeur of human understanding. Small as we are, we can conceive of, describe, and even explore, through imagination and instrumentation, these titanic voids. In the darkness of a black hole's shadow, we ultimately found not just terror, but enlightenment. We learned that even in finality, there is mystery, and in mystery, perhaps, an unexpected kind of continuity. Black holes have taught us that the universe is more creative and complex than our initial naive guesses, that it hides wonders in the places that look like pure destruction. They urge us to continue peering into the darkness, because who knows what we'll find? Maybe not oblivion, but the next great revelation. As we drift away from our imaginary perch at the event horizon, back to the safety of starlight and more familiar cosmic scenery, we carry with us the lessons and the awe black holes inspire. These objects, the most extreme endpoints of gravity, have become gateways to understanding fundamental truths. They show us the value of looking into the abyss and not flinching. And as long as there are horizons to cross, whether physical or intellectual, the spirit that drove us to understand black holes will drive us further, onward, into the unknown, turning even the darkest voids into light, silence, darkness. No stars, no ground beneath your feet, and perhaps not even the flow of time, just an infinite, motionless night. Imagine a void, with no up or down, no sound or motion. In that profound quiet, before anything begins, we find a fundamental question taking shape. What is the dark, yawning space that stretches out in all directions? Not the stars or planets that speckle it, but the space itself. The black canvas on which all cosmic lights are hung. What is space, when it stands alone, empty of all things? Since ancient times, people have looked into the night and pondered the void. Many mythologies begin with a great empty darkness from which creation arises, a cosmic egg in a vast sea, or a formless chaos giving birth to the world. In a way, modern science echoes those old intuitions. We too speak of an initial emptiness that blossomed into the universe we know. We usually imagine space as nothingness, a vacant expanse separating the stars. Even scientists once assumed it was merely an empty stage. In the 19th century, many thought an invisible ether must fill the void, a mysterious medium to carry light. But every experiment to detect this ether failed. Light needed no carrier at all. It moved through pure vacuum. Space, it seemed, could be truly nothing. And yet, if you listen closely to the silence, you may sense something more subtle. The void is not truly void. The darkness is not truly nothing. Space is a presence, an invisible fabric that underlies everything. It is quiet and transparent, so easy to ignore. Yet it is real, physical, and dynamic. Space isn't an empty backdrop, but an active, ever-present matrix. It can bend, it can stretch, it can ripple. About a century ago, our picture of space underwent a profound change. Experiments and new ideas revealed that space is not a fixed, unchanging void at all. It can warp and even participate in the cosmic dance. Gravity, we learned, is not a mysterious pull through nothingness, but a bending of space itself by mass. Space and matter interact continuously. Space is like the quiet canvas that holds a painting, or the pause that makes music melodic, an unseen framework that underlies and gives form to everything. Imagine placing a heavy ball on a taut rubber sheet. The sheet stretches and sags under the weight. In much the same way, anything with mass, a planet, a star, a galaxy, presses on the fabric of space. Space curves gently around it. What we feel as gravity is not a pull through emptiness, but the tendency of objects to slide down those curves. The Earth circles the Sun because the Sun dents the space around it, like a large marble sitting on a stretched cloth. Earth is not tethered by invisible strings. It is caught in the Sun's invisible indentation in space-time, moving along a curved path that to us appears as an orbit. In short, mass shapes the geometry of space, and space guides the motion of mass. Even light, which has no mass at all, follows the curves of space. Over 100 years ago, during a total solar eclipse, astronomers noticed that stars appearing near the eclipsed sun were slightly out of place. Their light had bent on its journey to us, detoured by the sun's warped space. It was a dramatic confirmation that space itself, curved by the sun's presence, was guiding the starlight. Today, we regularly use this effect, called gravitational lensing, to observe distant galaxies. A massive cluster of galaxies can act like a cosmic lens, its curved space bending the light of even more distant objects behind it. Sometimes we see a single galaxy smeared into an arc, or even a perfect ring of light encircling a closer galaxy cluster that is acting as the lens. These mirages are the unmistakable signature of space, behaving like a gigantic lens, bending and focusing the paths of light. Through these rings and arcs, we see space itself revealing its curvature to our eyes. If space can bend, it can also stretch. Indeed, the fabric of space has been steadily expanding since the primordial beginning of the universe. Distant galaxies are not just flying away through space. the space between us and them is itself growing. Early observers noticed that the light from remote galaxies is shifted toward the red end of the spectrum, as if the wavelengths have been stretched out. The farther a galaxy, the more its light is redshifted. The straightforward explanation is that space itself is expanding, carrying galaxies apart like raisins embedded in rising dough. Over billions of years, this expansion has enlarged the distances between galaxy clusters immensely. Another useful image is to picture space as the two-dimensional surface of a balloon, with galaxies like ink dots on that surface. As the balloon inflates, the dots move farther apart from each other. No single dot is the center of the expansion. Every dot sees the others receding. Likewise, in our three-dimensional space, every galaxy observes other galaxies rushing away. If we rewind this expansion in our minds, we find that in the distant past, everything was closer together. Galaxies crowd nearer, stars huddle closer. Far enough back, all the matter and light in the universe was crammed into a much smaller volume than today, a state of incredible density and heat. Space itself was compact and blazing with energy. There was a time when the entire young universe was like a hot, glowing fog. Imagine being present in that early inferno. No distinct stars or structures, just a blazing soup of particles and light everywhere you look. An intense white-orange glare filling all of space. As space expanded and thinned out, that searing brilliance faded to a gentler afterglow. Even now, space carries a memory of that fiery beginning. When we point sensitive instruments to the sky, we detect a faint glow of microwaves coming from every direction. This is the afterglow of the primordial fireball, the cosmic microwave background. It is the light from a time about 380,000 years after the Big Bang, when space had cooled enough for atoms to form and for light to travel freely. Since then, those light waves have been stretched by the ongoing expansion of space until they are microwaves, cooled to only a few degrees above absolute zero. Every patch of space is filled with this soft whisper of ancient light. It is almost perfectly uniform and smooth, but has tiny fluctuations, little freckles of slightly warmer and cooler spots, corresponding to minuscule density variations in the early universe. Those slight differences, on the order of only 1 part in 100,000, became the seeds for galaxies and clusters later on. It's as if the walls of the universe still faintly remember their incandescent youth. This ancient light also gives us clues about the overall shape of space. By studying subtle patterns in the microwave background, scientists have learned that on the largest observable scales, space is remarkably flat in its geometry. In a curved universe, those patterns would appear distorted, larger or smaller than expected, much as drawings on a balloon change size when the balloon is inflated. But observations show no such distortion. The angles of those primordial patterns add up just as they would in flat, Euclidean space. For example, in a universe shaped like a 3D sphere, a closed universe, two initially parallel beams of light would eventually converge and meet, and traveling in a straight line long enough could, in theory, loop you around to your starting point, just as an airplane circling the Earth arrives where it began. In a saddle-shaped or open universe, parallel beams would diverge and triangles would have angles summing to less than 180 degrees. But our measurements show nothing of the sort. This suggests that space, as far as we can measure, is not curved into a giant sphere or warped into an endless saddle. Instead, it stretches out in all directions without substantial overall curvature. Space is, to the best of our knowledge, flat and likely unbounded, or so vast that it might as well be infinite. It might extend infinitely, or perhaps it wraps around on a scale so colossal we cannot detect it. But within our cosmic horizon, space behaves like an endless level plane. To achieve such vast flatness and uniformity, the universe likely underwent an extraordinary growth spurt at the very dawn of time. According to the theory of cosmic inflation, a fraction of a second, on the order of 10 over 32 seconds or less, After the Big Bang, space itself expanded at a mind-boggling rate, doubling in size over and over in the blink of an eye. In that brief moment, what had been a microscopic region inflated to astronomical scales. A region smaller than a proton might have stretched to the size of a galaxy in an instant. This rapid stretching would have smoothed out any curvature or clumps, explaining why space now appears so flat and even on large scales. During inflation, tiny random quantum fluctuations, little blips of density in the microscopic early universe, were blown up to enormous sizes. Quantum fluctuations inherent to space itself, magnified to cosmic proportions, became the seeds of future structures. Regions of the young universe that had just slightly more matter or energy became, after inflation, entire huge regions with that slight edge. Those minuscule differences, perhaps only a few parts in 100,000 in density, gave certain patches of space a head start in gravitationally attracting matter. As the universe aged, those patches grew into the first galaxies and clusters. In this way, inflation planted the seeds of cosmic structure. The slight differences from one place to another, once infinitesimal, became the blueprint for all the galaxies, clusters, and voids that would later develop. Space, by expanding so fiercely, essentially cast the dice for the universe's future architecture, turning tiny quantum wrinkles into the grand pattern of stars and galaxies we observe today. When this furious burst of expansion ended, the energy driving it did not simply vanish. It transformed, heating the universe with a burst of radiation and particles. In essence, when inflation stopped, space unleashed its pent-up energy, igniting the hot Big Bang fireball that people often think of as the beginning of the universe. From that point onward, space continued to expand, but at a calmer pace, filled with a blazing plasma that would eventually cool into atoms, gas, stars, and galaxies. The rapid inflationary expansion set the initial conditions, and the slower expansion that followed allowed the cosmos as we know it to emerge. Inflation also opens the door to a startling idea: a multiverse. If the inflationary expansion happened in our region of space, it might have happened, or be still happening, in others. Some theories suggest that inflation never completely stops everywhere. While it ended in our patch, allowing our Big Bang and galaxies to form, in other regions space might still be inflating, or might have ended at a different time. Each of these regions could become its own universe, a bubble with its own galaxies, and perhaps even different physical constants. Our observable universe would then be just one bubble in a limitless foaming sea of universes. We have no way to directly see these other bubbles. They lie beyond any light we could ever receive. But the multiverse concept shows how our conception of space may extend even beyond the bounds of our own universe. Space, in this grand view, is an ever-expanding ocean, spawning countless cosmic islands. Whether this is true or not remains speculative, but it stretches our imagination of what space could be, not just the stage of one universe, but perhaps a prolific generator of many. Over billions of years following inflation, gravity worked on the tiny density variations left in the fabric of expanding space, drawing matter into clouds and clumps that would ignite as the first stars and galaxies. Galaxies pulled together into groups and clusters, and these linked up via filaments of gas and dark matter, forming a vast cosmic web. On the largest scale, the universe looks like a spider web or a sponge, dense clusters of galaxies connected by thread-like filaments, with enormous dark voids in between. Those voids, immense bubbles, millions of light years across, nearly empty of galaxies, are the regions that gravity emptied out as it drew matter into the filaments. In other words, most of the universe's volume consists of these yawning voids, with the galaxies tracing lacy patterns along their boundaries. It's a breathtaking structure, the invisible scaffolding shaped by gravity out of the expanding fabric of space, with over 80% of the volume of the universe contained in those silent voids. The lights of the stars and galaxies stand out like glittering nodes, but it is the darkness between them that dominates by volume. Now picture yourself in the middle of one of those cosmic voids, utterly removed from any galaxy. You are floating in intergalactic darkness, light years from the nearest star. Around you, the darkness is nearly absolute. Perhaps a faint, ghostly smudge of a distant galaxy is barely visible in one patch of sky, and another dim glow in the opposite direction. But to your unaided eyes, it would mostly be pure black. The nearest substantial galaxy could be tens of millions of light years away, so far that its light is unimaginably feeble. You are, for all practical purposes, alone in a silent, endless night. This is space at its most austere, a volume of the universe almost entirely devoid of matter. And yet, even here, space is not truly empty. A stray hydrogen atom might drift by now and then, or a thin breeze of particles from some far-off galaxy cluster might waft through. You would also be bathed in the ever-present microwave background radiation from the Big Bang, though you wouldn't sense it without instruments. In this void, you can viscerally feel that space is something real, a vast container with you at the center and almost nothing else around. It's a haunting, beautiful solitude. Such voids are the dark wombs of the cosmos, within which the bright filaments of the cosmic web are suspended. Gravity's architecture, the cosmic web of filaments and voids, is heavily influenced by a form of matter we cannot see, dark matter. Decades ago, astronomers measuring the speeds of stars in galaxies discovered a surprise. In galaxies like our Milky Way, the outer stars orbit the center far faster than expected, based on the visible stars and gas alone. They should have been flung off into space, but they remained bound. It was as if an extra unseen mass was providing the gravitational pull to hold them in. Likewise, galaxies in rich clusters move as though there is much more mass present than we can account for with the observed galaxies and hot gas. And when we observe gravitational lensing by a cluster, the bending of light is far stronger than visible matter alone can explain. All of this evidence points to a vast amount of invisible mass enveloping galaxies and clusters. We call this mysterious substance dark matter. It neither emits nor absorbs light, making it effectively invisible to our telescopes. Yet it outweighs ordinary matter by a factor of about 5. Dark matter forms huge halos around galaxies, extending well beyond the visible stars. Every galaxy, including our own, is embedded in a cocoon of this invisible material. Entire galaxy clusters are swathed in massive clouds of dark matter. Its gravity is what helped pull normal matter into the filaments of the cosmic web in the first place. Without dark matter's guiding gravitational pull, the universe's large-scale structure would have formed much more slowly and differently. We cannot see dark matter directly, but we see its imprint. Space curves around it, and galaxies move under its gravitational influence. Through these effects, the hidden scaffolding of dark matter in space becomes perceptible. Space is quietly filled with an unseen mass that shapes the universe profoundly. In the late 20th century came another revelation. The expansion of space is accelerating. After gravity built the cosmic web, one might expect that over time the pull of all those galaxies on each other would slow the expansion of space. And for billions of years, it likely did slow. But to great astonishment, we have found that in the last few billion years, the expansion of the universe has begun to speed up again. Distant galaxies are receding faster and faster as time goes on. Space is expanding not only steadily, but with an ever-increasing pace, as if some mysterious force is pushing it outward. We give the name dark energy to this unknown cause of cosmic acceleration. Unlike dark matter, which adds gravity, dark energy seems to act as a kind of anti-gravity on vast scales, a subtle pressure embedded in the fabric of space that drives it to expand faster. As space grows, more of this repulsive effect appears, since dark energy is thought to be a property of space itself, pushing galaxies apart with increasing strength. Today, dark energy dominates the universe's energy balance. Roughly 70% of the total contents of the cosmos appears to be this shadowy influence, with dark matter making up most of the rest. The ordinary matter, the stars, gas, dust, planets, and us, accounts for only a few percent. In an ironic twist, the emptiest thing, space, contains the majority of the universe's energy in this form. The silent void has an energetic underpinning that shapes the cosmos. What this means for the far future is profound. As space expands faster and faster, galaxies that are now visible will eventually slip beyond our cosmic horizon, their light stretched and diminished until they vanish from view. In tens or hundreds of billions of years, everything outside our local group of galaxies will have moved out of reach. The universe will appear to whoever remains as an empty void, with only the local galaxies, perhaps merged into one, in view. For example, in about 100 billion years, the galaxies of the Virgo cluster and beyond may be so far that their light never reaches the Milky Way region. After many hundreds of billions more years, even the nearest large galaxy, Andromeda, now destined to collide and merge with our Milky Way long before then, and its remnants would be far beyond detection. The expansion of space will carry all other islands of matter irretrievably away. What will the cosmos look like then? In that deep future, the observable universe will become dark and empty, with only faint whispers of local starlight remaining. Perhaps an astronomer living in that far future era on some distant world would peer into the sky and see nothing beyond her own galaxy. She might point her telescope outward and find endless blackness in every direction. All other galaxies would have faded beyond reach or redshifted into obscurity. She would have no way of knowing that a vast cosmos full of galaxies had ever existed. The cosmic truth we know today, that space teems with billions of galaxies, would be hidden from her by the relentless expansion of space. That future astronomer might conclude that her galaxy was the entire universe, a tiny island adrift in infinite nothingness. For us living in the present cosmos, the discovery of dark energy is a humbling reminder that what we once took to be empty nothingness can control the destiny of everything. The silent space between galaxies turns out to hold a secret power that shapes the entire evolution and future of the universe. Space, the quiet stage, has proven to be the hidden protagonist of the cosmic story. Before we return home, let us take an imaginary journey back through the cosmic expanse. Picture yourself out at the edge of a great cluster of galaxies, where hundreds of galaxies shimmer around you like a glittering swarm. Now you begin to travel back toward our own galaxy. As you move, galaxies drift past, scattered in the vast darkness. You glide along one of the filaments of the cosmic web that leads to the Milky Way, passing other island universes along the way. In the distance ahead, a faint band of light comes into view, the combined glow of billions of stars. Our Milky Way, seen from afar as a hazy, spiral disk of light. You approach it, crossing the immense gulf of intergalactic space. Now you plunge into the outskirts of our galaxy, rushing past sparse outer star clusters and the wispy halo of tenuous gas. The star density increases around you as you enter the Milky Way's disk. Entire clusters of young stars drift by. Great nebulae, stellar nurseries, glow softly in pink and blue. By the time you near the inner regions, stars surround you like a sparkling ocean. You weave through a spiral arm, passing magnificent blue-white giants and red supergiants, skirting around clouds of interstellar dust. In the distance, you spot a modest yellow star, our Sun, coming into view. As you draw closer, you see it is accompanied by planets orbiting in the plane of a thin, flat solar system. You sweep past the orbit of Jupiter, then Mars, And now the blue sphere of Earth appears. At this scale, it is a tiny, fragile-looking bead of blue and white, shining against the blackness. You home in on it, watching its oceans and clouds resolve into clarity. In moments, the planet looms large, its atmosphere a glowing thin shell. You slip gently into that atmosphere, experiencing the rush of air as you descend, and finally come to rest on Earth's surface, back to the soft familiarity of ground beneath your feet. Your fantastical voyage from the end of the universe to our home is complete. Now, having roamed the vast reaches of the cosmos, let us gently return our focus to something more intimate, the space around and within us. We leave the clusters of galaxies and zoom back toward a single galaxy, our Milky Way, and then to a particular star, our Sun, with its family of orbiting planets. Between those worlds stretches millions of kilometers of space, populated only by sparse dust and the thin wind of charged particles from the Sun. Closer in, we see the blue marble of Earth, surrounded by the gauzy blue halo of its atmosphere. From high above, Earth appears as a delicate blue-white sphere hanging in the blackness. Our atmosphere, a thin film of air and cloud, clings to its surface and gradually merges into space. Only a few hundred kilometers up, the air becomes so tenuous that space begins. Beyond that, the sky fades to black. In truth, there is no sharp boundary where space starts. The air just thins more and more until there is effectively none. But effectively, just above the blue sky, the true vacuum of space begins. Only a fragile veil of atmosphere separates us from the cosmic void. There, in low Earth orbit, astronauts aboard space stations witness directly the stark contrast between the bright Earth below and the utter blackness above. They float in microgravity, essentially falling around Earth, immersed in space. When they look up, away from Earth, they see endless darkness spotted with stars that do not twinkle because there is no air up there to flutter their light. The sun shines fiercely without the softening filter of atmosphere, and the divide between day-lit Earth and night-shadowed Earth is a sharp line across the globe. Those astronauts live on the very boundary of space, inside a thin bubble of air in their spacecraft that separates them from the vacuum outside. They often describe the experience as deeply humbling. Above them, an infinite void. Below them, the jewel of Earth with its thin blanket of air. During spacewalks, when they step outside into the vacuum, wearing only a protective suit, they can feel the profound silence and isolation of space. No sound, no breeze, only the distant curve of Earth and the raw, brilliant stars. For them, space is not a theoretical concept, but a palpable reality. They understand in their bones that space is here, around us, an ever-present ocean, just a breath beyond our daily reach. We descend back to the surface now. Picture yourself standing on a quiet night field, looking up at the stars. Although you feel solid ground underfoot and air on your skin, you are as much in space as an astronaut floating in orbit. The space around you is simply filled with a thin mixture of gases, our atmosphere. If you could magically remove all that air, the vacuum that remains would be continuous with the vacuum between the planets and stars. There is no wall or border between space down here and space up there. It is one connected expanse. The same space that stretches between galaxies is present in the room around you, between the walls and among the molecules of air. We truly have never left space. We live at the bottom of a shallow ocean of air, but that ocean is itself embedded in space. People often talk about going into space as if it's somewhere else, but space is already here. Step by step, as you climb a mountain or rise in a balloon, the air thins and space reveals itself. Astronauts in orbit are not in a different realm. They have merely ascended above most of the air, into the naked vacuum that was there all along. Space is not distant. It is the backdrop of our existence, even here on Earth. Even our everyday experiences are dialogues with space. Take a breath. You inhale molecules of air that moments ago were scattered across the room, and you exhale molecules that will disperse outward. In doing so, you are stirring the space around you. The air filling your lungs quickly mixes and returns to the atmosphere, ultimately diffusing into the great expanse. In a very real sense, space is the medium through which life interacts with the world. Every movement you make is a displacement in space. Every sound you hear travels to you through vibrating molecules in space. Out in the near-total vacuum beyond Earth's atmosphere, there is no air to carry sound. In space, no one would hear you scream. It is truly silent out there. Every sight you see is brought to your eyes by light crossing space. Space is not an abstract backdrop to life. It is intimately involved in every aspect of our being. Consider even more deeply, you yourself are largely made of space. The atoms in your body are mostly void, their mass concentrated in tiny nuclei, and their size defined by electrons moving through emptiness. If all the empty space in your atoms were somehow removed, you would collapse into a speck far too small to see. And of course, without that space, you wouldn't exist as a living being at all. It is the spacious architecture of your atoms that allows them to bond into molecules, and molecules to build cells, and cells to form a living organism. Thus, space is inside you as much as you are in space. It provides the room that your particles and forces need to operate. We begin to see a pattern from the vast distances between galaxies down to the tiny gaps within atoms. Space is there, quietly doing its work. It provides room for structure to exist, for planets to orbit, for light to travel, for atoms to join and form molecules. The emptiness is not a flaw or an absence. It is an essential ingredient. It allows separation and form. Without the gulf of space within each atom, there could be no distinct atoms and no chemistry, no solid matter as we know it. Without the reaches of space between stars, gravity could not isolate individual worlds where life might arise. Space is the great enabler, the silent canvas that allows matter to take shape and motion to have meaning. Just as a clay pot's usefulness lies in the empty space it encloses, the utility of the cosmos lies in its gaps and hollows. An empty cup holds water. The emptiness within an atom allows it to bond with others. In both cases, what is not there enables what is there to function. And what about space at even smaller scales? Far smaller than an atom, smaller than the tiniest subatomic particle. Here we approach deep mysteries. Physicists suspect that if you zoom in far enough, space itself becomes turbulent and uncertain. On the scale of the Planck length, about 10 to 35 meters, the very concept of distance might break down. Space might dissolve into a kind of quantum foam, with the smooth fabric of space-time becoming frothy and indeterminate. At that scale, according to some ideas, tiny bubbles of space-time could appear and vanish, and geometry itself might fluctuate wildly. Wheeler, a physicist, famously imagined the scene as the quantum foam, a churn of space-time at the smallest scales. Over sufficiently small distances and brief moments, the smooth geometry of space and time could erupt into a storm of random fluctuations. Imagine zooming into what looks like a smooth photograph, only to find it grainy with pixels at a certain magnification. These fluctuations could be large enough, on those scales, to cause significant departures from the smooth space-time we perceive at human scales, giving space a foamy, jittering character when examined ultramicroscopically. With our current technology and understanding, we cannot probe such minute scales directly. Our best theories, quantum mechanics and general relativity, don't play nicely together at this extreme, so we don't yet have a clear picture of what space truly looks like at the Planck scale. It's possible that space-time is not fundamentally smooth. It might be made of countless tiny units or threads. There is no definitive reason that space needs to be perfectly continuous. Perhaps, in a full theory of quantum gravity, space-time would consist of many small, ever-changing regions where space and time themselves blur and fluctuate. It's a mind-bending idea. The familiar continuity of space might, under magnification of 1033, break into a ceaseless fizz of tiny distortions and ephemeral particles popping in and out of existence. Yet black holes are not absolutely black. Quantum theory predicts that the vacuum near the event horizon of a black hole seethes with particle-antiparticle pairs. Occasionally, one particle from such a pair can be pulled into the black hole while the other escapes. To an outside observer, the black hole appears to emit a faint trickle of particles, a phenomenon known as Hawking radiation. Over inconceivably long periods, this process can cause a black hole to slowly evaporate, leaking its mass back out into space. This is another reminder that even the empty space near a black hole is full of activity. The vacuum isn't void at all. Its quantum fluctuations can have tangible effects, bleeding away the black hole's mass bit by bit. In this way, space acts as both giver and taker, swallowing light at the horizon, yet furtively returning energy to the universe through quantum processes. One place where we suspect this quantum nature of space becomes crucial is inside black holes, those mysterious abysses formed from collapsed stars. A black hole is a region where space is curved so extremely that once anything, matter or light, falls in, it cannot escape. The boundary around a black hole is called the event horizon. At that boundary, space is rushing inward at the speed of light, like a waterfall of space-time cascading into the hole. If you approach the horizon, time slows relative to the outside world, and the pull of gravity, the curvature of space, becomes overwhelming. To a distant observer, you would appear to slow and dim, never quite falling in, as your final light waves get stretched and weakened, a strange visual consequence of the way space and time warp. Beyond the horizon, all paths lead further inward, deeper into the hole. As you fall inside a black hole, you would experience space rushing you inexorably toward the center. According to general relativity, at the very center lies a singularity, a point of infinite density where space and time, as we know them, ends. In truth, this singularity is likely where our current understanding fails. Gravity is so extreme and the scale so tiny that quantum effects should dominate. Here, the smooth fabric of space might tear or blend with the quantum foam. The distinction between space and matter could blur. We don't yet have a theory of quantum gravity to tell us exactly what happens in such an intense intersection of the very large and the very small. Does space cease to exist as a meaningful concept at the core of a black hole? Are there atoms of space-time or quantum threads knitting things together beyond our view? We simply don't know. The laws of physics as we have them break down in these conditions. Physicists have proposed bold ideas to reconcile these deep conflicts. One radical suggestion is that space and time might not be fundamental at all, but rather emerge from something more basic and abstract. Some research hints that quantum entanglement, the ghostly interconnection between particles, may knit together the fabric of space itself. In certain theoretical models, the geometry of a region of space can be described entirely by the information, the entanglement connections, on its boundary. This is known as the holographic principle, suggesting that our three-dimensional space might in some way be a projection from information encoded on a distant two-dimensional surface. It's as if space could be woven from quantum threads of information. Another idea is that space-time is composed of tiny, discrete units, sometimes envisioned in approaches like loop quantum gravity, so that on the smallest scale, space is more like a woven lattice or network. These concepts are still speculative and hard to test, but they share a poetic point. They hint that space, for all its apparent continuity, might be an emergent illusion, like a tapestry that looks smooth from afar, but up close is made of fine threads. If so, there could exist degrees of freedom or building blocks of the universe more fundamental than space and time. What is space, truly? It may be that our familiar space is just the visible frosting on a much deeper reality. Facing these profound questions, humanity has responded by inventing clever ways to probe the nature of space. We have built powerful telescopes that peer across billions of light years, effectively allowing us to look back in time and see the young universe when it was filled with hot plasma and newly formed galaxies. We have launched observatories above our atmosphere to measure the cosmic microwave background with exquisite precision, mapping its faint ripples to decode how space expanded and what it contains. We have devised experiments on Earth to test the nature of the vacuum. For instance, sensitive laboratory apparatus has confirmed the Casimir effect, detecting the slight pressure of vacuum fluctuations pushing two plates together. We smash particles together in giant accelerators, momentarily concentrating tremendous energy into tiny volumes of space, to glimpse how nature behaves at the highest energies and smallest scales. This endeavor led to the discovery of the elusive Higgs field that permeates space and endows particles with mass. We have even detected the subtle ringing of space-time itself using gravitational wave observatories like LIGO. These giant laser interferometers can sense when space stretches and squeezes by less than a trillionth of a centimeter as a gravitational wave passes. The first such detection in 2015 came from two merging black holes and was heard as a faint chirp, literally the sound, after conversion, of space briefly vibrating from a cosmic collision. Since then, we have caught multiple cosmic events via gravitational waves, black holes swallowing each other, neutron stars colliding and sending tremors through space. It's a completely new way of listening to the silent universe, using space itself as our messenger. We have also physically journeyed into space, albeit only a small distance so far in cosmic terms. Our robotic probes have ventured beyond the planets, sampling the environment of space directly. The Voyager 1 and 2 spacecraft, for example, have traveled beyond the influence of our sun's solar wind and entered interstellar space, the space between the stars. They confirmed that even the emptiest regions of our galaxy are not entirely empty. They contain traces of very thin plasma, ionized gas, and high-energy cosmic rays. Voyager 1, now over 23 billion kilometers away, is humanity's farthest messenger. It is sailing through the cold, silent void, reporting back that even out there, far from any star, there are a few atoms per cubic centimeter and faint whispers of magnetic fields and radiation. Its journey reminds us that space is not a distant void we go to. It's the ocean we've always been swimming in, now stretching out to greater and greater depths. We are not outsiders to the universe's expanse. We are an integral part of it. We move through space. We depend on it. We are composed of it. In a sense, we, conscious beings, are space's way of observing itself, the universe contemplating its own vastness through our eyes. From the space between galaxies to the space inside your chest, it is one continuous fabric. The next time you gaze up on a clear night and marvel at the darkness between the stars, remember that that darkness is not empty. It is the same space that cradles you, extending through and around you always. We tend to think of ourselves as down here and space as out there. But in truth, we have always been in space. From the moment of our birth, we have been enveloped by space. Space is not a distant domain only astronauts visit. It is the vast, subtle medium in which we live and breathe. When you look up at the night sky, you are looking into an extension of your own surroundings. The air ends not far above your head, and then space continues, unbroken, to the ends of the universe. So, what is space? It is not a mere nothingness, not a sterile void. It is the gentle scaffolding that holds all of creation. It is a medium that can bend and ripple, a vast field that carries light and nourishes the formation of stars. Space is the silence that allows the music of existence to be heard. It is the canvas on which the galaxies are painted. And yet the canvas itself has texture and influence beyond what our eyes see. Space is the invisible architecture of the universe, the foundation that connects all things. It is often said that nature abhors a vacuum, but in truth, nature uses the vacuum, space, as the foundation for everything. Without space, there would be no room for light to travel, no separation for objects to exist apart, no time for events to unfold. Space is not the absence of things. It is the presence that allows things to be. It is the very possibility of anything and everything. As our journey through darkness and light comes to an end, we return to that initial quiet question and find a profound answer. Space is not an emptiness to be feared, but a presence to be revered. It is the quietly fertile nothing that makes everything possible. We float in it, we are made of it, and we are forever embraced by it. The invisible architecture of the universe surrounds and sustains us. Space is the darkness that cradles the stars, the silence that gives meaning to sound, the stillness that makes motion possible. It is the vast, living fabric in which the story of the cosmos and our own story is written. Space is the womb of the universe, the canvas of creation. It is not an absence, but the gentle yet all-encompassing presence that allows all things to be. There was darkness. For a long age after the birth of the universe, no stars shone, no galaxies twirled, only darkness and silence stretching across an unfathomable expanse. The cosmos was newborn and without form, filled with diffuse clouds of hydrogen and helium gas, remnants of the Big Bang. There were no twinkling lights, no warmth, only the faint afterglow of creation cooling into night. Imagine that primordial darkness, a universe waiting, quiescent and still, with all its future potential sleeping in invisible clouds. But even in that silence, gravity was at work. Slowly, imperceptibly, it drew the primordial gas into filaments and clumps, coaxing the first structures to form in the void. Over eons, these clumps grew denser and hotter at their centers. Deep within one such gathering of gas, pressure and heat built until something new and miraculous occurred. Nuclear fusion ignited. There, in the bleak darkness, a tiny point of light flared into being. The first star had been born. In that moment, the universe was no longer lightless. A spark had appeared in the cosmic night. With that first star, the cosmic dawn broke. One solitary star poured out light and heat, pushing back the blackness around it. And soon, another star lit, and then another, scores of them, flickering on in the cosmic night. What had been endless darkness was now speckled with faint starlight. These first stars were unlike the stars we know today. They were giants of pristine hydrogen and helium, born in a virgin cosmos. They burned with brilliant blue-white fire, immensely hot and massive. Their intense ultraviolet light flooded into the surrounding gloom and began to clear away the primordial fog of neutral hydrogen that filled space. For the first time, light moved freely through the cosmos, illuminating it on a grand scale. The cosmic dark ages were ending. The universe was beginning to reveal itself in starlight. These first stars lived fast and died young. After only a few million years, brief by cosmic standards, their central fuel was exhausted. In their cores, they had fused hydrogen into helium and helium into carbon and other heavier elements, forging the first atoms of carbon, nitrogen, oxygen, and more. When fusion could proceed no further, the balance that held them up faltered. The stars met their end in colossal explosions. One by one, the primordial giants tore themselves apart as supernovae. Each such explosion was titanic. Momentarily, a single star's death could outshine an entire galaxy. The night that had been gently lit by starlight was suddenly ablaze with a ferocious flash. Then, as the supernova faded, darkness returned. But it was not the same darkness as before. Now, it was enriched by the scattered ashes of stars, the gaseous debris of those first supernovae, carrying newly forged elements mixed back into the cosmic gas, seeding the universe with the ingredients for future worlds. Meanwhile, gravity continued its creative work on larger scales. The first stars had formed in small protogalactic clumps, and gravity drew these clumps together. They merged and coalesced into the first galaxies, swirling assemblies of stars, gas, and dark matter. The once empty universe was now dotted with infant galaxies, and each new galaxy sparkled with the light of millions of stars. Over billions of years, galaxies grew by merging with each other and forming new stars within. The cosmos transformed from a dark, simple expanse to a richly structured tapestry. By a few billion years after the beginning, the cosmic web of galaxies stretched across space, filaments of glimmering light tracing gravity's hand. Generation after generation of stars continued to be born and die within these galaxies, steadily enriching and shaping them. The universe's early thin gases had become a complex network of stellar cities, glowing with billions of points of light. Let us drift into one such galaxy, a spiral galaxy not unlike our own Milky Way, at a time when the universe is mature and full of stars. Within one of its graceful spiral arms lies a vast, cold cloud of molecular gas and dust, tens of light years across. It is dark and opaque, a silent nebula hiding new wonders inside. This is a stellar nursery, a place where new stars will be born. For ages, this cloud has floated in the galactic disk, nudged by passing spiral density waves and perhaps stirred by ancient supernova shockwaves. Now, regions within it begin to collapse under their own gravity. Deep inside, dense knots of gas form, each destined to become a star or a group of stars. All through the cloud, multiple embryos of stars are taking shape, though they are hidden from view by the dusty shroud. In one region, a particularly dense clump, perhaps a few dozen times the mass of our Sun, contracts and fragments. At its center, material compresses into a smaller, hotter protostar. Change is coming to the darkness of this nebula. At first, the forming star is shrouded. It is a protostar, not yet fully born, growing as it pulls gas from the surrounding cloud. It spins faster as it contracts, and a rotating disk of gas and dust forms around it. Twin jets of hot gas shoot out from its poles, tunneling through the cloud. Deep inside, the temperature climbs higher and higher. For tens of thousands of years, a mere moment in cosmic time, this protostar gathers mass in the darkness, heating up steadily. When its core temperature reaches about 10 million degrees, a great transformation occurs. Hydrogen nuclei begin to fuse into helium. In a sudden burst of energy, true starlight ignites in the core. The protostar has become a star. Outward pressure from this newborn star's core now halts any further rapid collapse. The star's fierce light and stellar winds blow away the cocoon of dust and gas that enveloped it. At last, the new star emerges from its birth nebula, announcing itself with brilliant light. The surrounding leftover gas, bathed in the star's intense ultraviolet radiation, begins to glow. What was once an invisible, cold cloud now shines as an ionized nebula, like a cosmic neon sign, its hydrogen gas fluorescing pink and red. A dark corner of the galaxy has given birth to a beacon of light. In the surrounding cloud, other newborn stars are likely emerging as well, turning the nebula into a cradle of suns. Indeed, stars are often born in litters. The collapse of one part of a cloud usually means many fragments produce protostars in the same region. As our star bursts forth, it is joined by dozens or hundreds of sibling stars, all coming to life together from the same cloud. Together, they form a young star cluster, a sparkling group of newborn suns of various masses. They blaze hot and blue, their combined radiance blowing the remaining nebula material into filaments and wisps. One can imagine the scene, where there was darkness and dust. Now there is a cluster of radiant stars, their light reflecting and refracting in the thinning veil of gas. The stellar nursery has become a celestial nursery rhyme of light, a beautiful, chaotic region celebrating the arrival of new stars. For a time, these siblings remain clustered, bound by the gentle gravitational pull they exert on each other. They drift together through the galaxy as a loose family known as an open cluster. In the cluster's early life, it is a stunning jewel box of brilliant stars, all relatively close in space. Yet, over hundreds of millions of years, this family will gradually disperse. Gravitational nudges from passing stars and clouds, as well as internal interactions, will cause members to wander away one by one. The cluster's members, once tightly knit, become strays, settling into their own orbits around the galaxy, mingling with billions of other solitary stars. This is the fate of most open clusters. They are transient gatherings that eventually dissolve into the galactic population. Our own sun likely shared this fate. It was almost certainly born in a cluster with many siblings, stars that formed from the same cloud some 4.6 billion years ago. Over time, that original cluster dissolved. Today, the sun roams the galaxy alone, and the stars that were born alongside it have long since scattered. A few of the sun's lost siblings may have been tentatively identified by their chemical signature, but most are strangers now far across the sky. Still, it's a profound thought. The sun's family of origin has dispersed, yet the galaxy is now sprinkled with those related stars, each carrying the same ancestral imprint in their atoms. In a sense, every star eventually becomes an orphan, blending into the vast community of the Milky Way. Some star clusters, however, are so massive and tightly bound that they can survive for billions of years. These are the globular clusters, ancient, spherical hordes of stars that reside in the outskirts, halo, of galaxies. A globular cluster might hold hundreds of thousands of stars crammed into a ball only a few hundred light-years across. The stars inside are extremely old, many formed during the early eras of the galaxy. They shine mostly with a warm reddish glow, having long ago lost their bluer, short-lived members. The stars in globular clusters are almost pure hydrogen and helium, containing only tiny traces of heavier elements, which tells us they were born before later generations of stars had seeded the galaxy with metals. They are truly relics of the distant past, cosmic time capsules unchanged for eons. If you could stand on a planet inside a globular cluster, the night sky would be a breathtaking spectacle. Thousands of stars would crowd the heavens, many so bright that even at night they could cast subtle shadows. There might be no true darkness at all. Your sky would be awash with perpetual starry twilight. These ancient clusters have witnessed nearly the entire history of the universe. Some of the stars shining around you in that cluster may have been burning since shortly after the galaxy itself formed. Globular clusters endure as splendid beacons on the fringes of galaxies, their stars bound together in a tight gravitational embrace for billions upon billions of years. Now let us return to our star, the one we followed out of its nebula. It has left its nursery and cluster behind, or its siblings have all drifted away. The star has entered the long, steady adulthood of stellar life. Deep in its core, hydrogen fusion generates a steady outpouring of energy. This energy travels from the core through radiative layers and convective currents, and finally radiates from the star's surface as light and heat. Gravity pulls inward on the star's mass, but the pressure of hot gas and the continuous fusion-powered radiation push outward. These forces balance perfectly. The star settles into a stable state known as the main sequence, where it will spend the majority of its life, shining at a nearly constant brightness for eons. It is as though the star has found harmony, a peaceful equilibrium in which it neither collapses under gravity nor erupts from internal fire, but simply glows steadily. Our Sun is in this very phase of life. It is a middle-aged main sequence star, quietly fusing hydrogen into helium in its core, as it has for about 4.5 billion years, and will continue to do for roughly another 5 billion. Day after day, it shines with reassuring consistency, its energy nurturing the planets orbiting it. We live in the warm embrace of a stable star. The sunlight that bathes Earth each day is the product of that core fusion, photons freed from the sun's interior after thousands of years of random walk and an 8-minute sprint across space to our world. This steady radiance has allowed life to arise on Earth, anchoring our existence. The sun, in all its ordinariness, means everything to us, yet the sun is just one of countless stars on the main sequence, doing the same quiet work across the galaxy. Even the sun has its subtle rhythms. Its surface seethes with convection, and dark magnetic blemishes called sunspots come and go. Approximately every 11 years, the sun's magnetic activity cycles, leading to periods of many sunspots and flares followed by lulls. Sometimes great arcs of plasma erupt from its surface in solar flares or coronal mass ejections, sending streams of charged particles into space. When these particles wash over Earth, they can spark auroras that dance in our polar skies, a vivid reminder that our seemingly gentle sun has its storms. Still, these variations are minor on the scale of the sun's total output. To our eyes and lives, the sun remains a stable beacon. It is a calm star by cosmic standards, and that calm has been essential for life on Earth to thrive over geological timescales. Not all stars enjoy such tranquility or longevity. The destiny of a star is determined largely by its mass at birth. Mass is the master parameter that dictates a star's temperature, brightness, and lifetime. A very massive star lives dramatically. It burns its fuel at a furious rate, shines brilliantly, and dies young. A small star lives cautiously. It sips fuel slowly, glows gently, and may outlive all other stars. Consider a star 10 times the sun's mass. Its core temperatures are far higher, and it will blaze blue-white, pouring out energy hundreds of thousands of times faster than the sun. But it might last only 20 million years before exhausting its core fuel. Now consider a star 1/10 of the sun's mass, a red dwarf. It is cool, perhaps 3,000 K at the surface, and dim, maybe 1/1000th the sun's luminosity. It will burn its hydrogen so frugally that it can live for hundreds of billions or even trillions of years. The universe itself is not old enough for any such star to have died yet. None of the red dwarfs born at the dawn of time have even begun to flicker. In short, massive stars are the sprinters of the cosmos, and red dwarfs are the marathon runners. Astronomers classify stars by their spectra and temperature. The hottest, most massive stars are O-type, glowing bluish-white and searingly bright. After O come B and A types, still extremely hot and white. F and G-type stars, our Sun is a G-type, are intermediate, white to yellow in color and moderate in heat. K and M stars are cooler, orange to red in hue, including the countless red dwarfs. This sequence, O, B, A, F, G, K, M, is essentially a temperature scale from the fiercest blue-white stars to the faintest red stars. And indeed, the night sky shows this variety. Some stars shine with an icy blue tint, others with a golden glow, and some with a faint reddish light. Each color is a clue to a star's inner furnace. A blue star is like a roaring fire. A red star is like a warm ember. The cosmos offers a grand palette of stellar colors and intensities. The sizes of stars also span a tremendous range. Some red supergiant stars have bloated to astonishing dimensions, as much as 1,000 times the Sun's radius. If one of those sat where our Sun is, its swollen atmosphere would extend beyond the orbit of Mars, perhaps even reaching Jupiter. By contrast, the smallest stars, just above the threshold for sustained fusion, are only a bit larger than the planet Jupiter. One of these tiny red dwarfs, while containing perhaps 8% of the Sun's mass, might measure only a tenth of the Sun's width. Between these extremes lie stars of every conceivable size, from giant stars big enough to engulf orbits of planets, to humble dwarves barely bigger than gas giant planets. The diversity is staggering. And if an object is smaller still, below about 8% of the Sun's mass, it never becomes a true star. It becomes a brown dwarf, a failed star. Such an object doesn't reach the core temperature needed for sustained hydrogen fusion. A newborn brown dwarf may briefly fuse a little deuterium, a heavy form of hydrogen, or simply radiate leftover heat from its gravitational contraction. But before long, it settles into a life of slowly cooling and fading. Brown dwarfs are like cosmic embers. They glow faintly in red or infrared light, but no fire rages within. They fill the gap between the largest planets and the smallest stars. In the galaxy, there may be as many brown dwarfs as stars, lurking dimly in the darkness, detectable only by sensitive infrared eyes. They remind us that nature's categories are fluid. There is a continuous spectrum from planets to stars, with brown dwarfs bridging the two. To the unaided eye across human lifetimes, most normal stars shine with a steady light. But many stars are not truly constant. Some vary in brightness in subtle or dramatic ways. Some stars pulsate in and out like cosmic heartbeats. A classic example is a Cepheid variable, a bright giant star that rhythmically swells and shrinks, causing its brightness to rise and fall over a period of days or weeks. When it expands, its surface cools and it dims slightly. When it contracts, it heats up and brightens. These pulsating stars are so regular that astronomers use them as distance markers. Their pulse period relates to their true luminosity. So by observing their cycle, we can deduce how far away they are. They literally blink out a Morse code that we have learned to read, helping us measure the universe. Other stars vary more erratically. Young stars, still surrounded by disks of gas, can flicker as they accrete material, or as clumps of dust periodically obscure them. Some mature stars erupt in flares, especially red dwarfs, which can unleash powerful stellar flares that make the star momentarily much brighter. Even our Sun is slightly variable. Over its 11-year sunspot cycle, its energy output changes by a fraction of a percent. And in old age, many stars become variable again. Red giants often pulsate with large amplitudes, like mirror variables, taking many months to cycle through a dimming and brightening. Such an elderly star might expand and contract so much that it visibly changes brightness over the course of a year, shedding its outer layers with each pulse. In some cases, a star's light is not changing because of its own behavior, but because of an external effect. Consider binary star systems aligned in our line of sight. When one star passes in front of the other, it eclipses its companion. From Earth, we see the combined light dip periodically, even though each star's intrinsic output is steady. These eclipsing binaries produce regular patterns of dimming and brightening, a stellar blink that can be clockwork precise. By studying such systems, astronomers can learn the sizes of stars and their orbits. In fact, the discovery of planets orbiting other stars often comes from a similar effect. A planet passing in front of its host star causes a tiny eclipse, a minute drop in the star's brightness. Sensitive telescopes can detect that dip, revealing the presence of a world we cannot otherwise see. In this way, the light of stars encodes the presence of their companions, be they other stars or orbiting planets. Indeed, many, perhaps most, stars are not solitary like our Sun, but part of binary or multiple star systems. Two stars bound together will orbit a common center of gravity, like dancers linked by an invisible string. If they are well separated, each evolves individually. But if they orbit closely, their lives can become intertwined in remarkable ways. Imagine a close binary where one star ages faster and swells into a red giant, while the other is still a smaller main sequence star. As the giant grows, its outer layers draw ever closer to the companion star. Eventually, the giant's gravity can no longer hold on to those distended layers. Its material starts flowing onto the companion. A stream of gas begins to pour through the inner Lagrange point, the gravitational gateway between them, forming a luminous accretion disk around the smaller star. Matter spirals in, heating up and glowing brilliantly. The giant star, losing mass, shrinks back somewhat, relieved of its burden, while the companion star gains fresh fuel and becomes hotter or more active. This mass transfer dramatically alters the fate of both stars. If the receiving star in such a scenario is a white dwarf, the dense core of a previously sun-like star, the story takes another turn. The gas dumped onto the white dwarf piles up on its surface. Over time, perhaps years or centuries, enough hydrogen accumulates on the white dwarf surface to trigger a sudden burst of fusion. In a flash, the layer of accreted gas ignites and detonates, causing the white dwarf to erupt in a nova. The star system that was faint brightens drastically for a little while, as the white dwarf's surface explodes in a thermonuclear flash visible across light years. After venting that energy, the white dwarf settles down and the cycle can begin anew if more gas comes in. In this way, a close binary can produce repeated novae like a recurring stellar heartbeat of explosive energy. In some cases, the white dwarf accumulates too much mass from its companion, beyond a critical limit, about 1.4 times the mass of the Sun. Then the entire white dwarf is overwhelmed by runaway fusion and detonates in one titanic explosion, a Type Ia supernova. In that instant, the white dwarf is obliterated, and a fireball of debris expands outward. Such a supernova can briefly rival a whole galaxy in brightness. Nothing of the white dwarf remains, only a rapidly expanding cloud of ash, rich in iron and nickel, hurtling through space at thousands of kilometers per second. These Type Ia supernovae are incredibly important standard candles in astronomy, yet behind their brilliance is the quiet story of a binary companionship that went to the extreme. Other binary destinies include outright mergers. If two stars in a binary spiral closer, perhaps due to gravitational wave emission or interactions with other stars, they can eventually collide and coalesce. Two main sequence stars merging will produce a single, more massive star, often with a spectacular transient event. Astronomers have observed luminous red novae, believed to be the signature of merging stars. The pair slowly draw together, then suddenly brighten with a red glow as they meld into one. The result might be an oddly bloated star or a fast-spinning object, but a new single star nonetheless. If, on the other hand, the binary is two neutron stars, the dense remnants of supernovae, their merger is even more dramatic. They collide and merge into either a heavier neutron star or a black hole, releasing a burst of energy that can include intense gamma rays and gravitational waves, literally a ripple in space-time that can be felt across millions of light years. Such a merger also forges heavy elements, like gold and platinum, in profusion, seeding the surrounding space with these precious materials. Thus, even in their deathly collision, stars create and share new riches with the cosmos. For long periods in between such events, a solitary star like our Sun just keeps shining steadily. But eventually, even the most stable stars must face an end to their fuel. Our Sun, for instance, after roughly 10 billion years of main sequence life, will deplete the hydrogen in its core. So what happens when a star runs out of its most basic fuel? The answer unfolds in stages, heralding the transition to a star's old age and death. For the Sun and stars of similar mass, this final chapter is both gentle and beautiful. For more massive stars, it is violent and spectacular. When a star like the Sun exhausts the hydrogen in its core, fusion in the core ceases, but fusion still goes on in a shell of hydrogen around the now inert helium core. With the core no longer generating outward pressure, it begins to contract under gravity. That contraction releases gravitational energy, which heats the core and the surrounding shell of hydrogen. The hydrogen shell, now hotter and under higher pressure, burns even more vigorously than the core did. The increased energy output pushes the star's outer layers outward. The star's envelope balloons to enormous proportions. As it expands, the star's surface cools because the same energy is radiating from a much larger area, and its hue shifts toward red. The star has become a red giant. Our sun will go through this transformation, swelling perhaps 100 times its current diameter. In those far future days, the sun's reddish orb could engulf Mercury and Venus, possibly even reaching close to Earth's orbit. Even if Earth is not swallowed, the sun's expanded atmosphere and intense heat would scorch our planet barren. In any case, the inner solar system will be radically transformed. A person, if somehow observing from a safe distance, would see the sun change from a small yellow disk to a vast, ruddy sphere that dominates the sky. The once stable star becomes a bloated giant, its core an intensely hot, contracting ball of helium ash. Its outer layers diffuse and cool. Yet paradoxically, the sun will shine more brightly overall during this red giant phase because its enormous size more than compensates for the cooler surface. It will be majestic and terrifying all at once. Inside the core of the red giant sun, temperatures continue to climb as the core contracts under gravity's relentless squeeze. When the core reaches about 100 million degrees Celsius, a new kind of fire is kindled, helium fusion. 3 helium nuclei begin fusing together to form carbon in a process called the triple alpha reaction. In stars like the Sun, this onset of helium fusion can occur very suddenly in what's known as a helium flash, releasing an enormous burst of energy in a matter of minutes. However, that energy mostly goes into lifting and expanding the core, not into blowing the star apart. The Sun will then settle into a new equilibrium, a helium-burning star. The core expands and cools slightly after the helium flash, and the star's outer layers contract a bit from their extreme red giant state. The Sun will become a somewhat smaller, though still large, yellow-orange giant, with a core quietly fusing helium into carbon and oxygen. This helium-burning phase is much shorter than the hydrogen-burning main sequence, perhaps only a few tens of millions of years for a star like the Sun. Eventually, the helium in the core is exhausted as well. Now the core of the Sun will be made primarily of carbon and oxygen, the ashes of the helium-burning phase. The core again lacks an energy source and begins to contract yet further. For a star of the Sun's mass, it will not reach the temperature needed to ignite carbon fusion. Fusion will continue only in shells around the core, a shell of helium fusing into carbon just outside the core, and a shell of hydrogen fusing into helium above that. The star responds by expanding again. It enters a second red giant phase, the asymptotic giant branch phase, swelling even more dramatically than before. The Sun will become extremely large and luminous, but also unstable. Its outer layers are only loosely bound now, and strong pulsations set in, causing the star's brightness to vary and its layers to puff outward and then fall back cyclically. During this time, the Sun, or any star in this phase, will begin to undergo significant mass loss. Each pulsation in the star's envelope helps throw some gas into space. The star also generates a slow but intense stellar wind, a stream of particles that drags away the star's outer atmosphere. The once robust star is quite literally blowing itself apart, bit by bit. Over tens of thousands of years, the Sun will shed a substantial fraction of its mass. Those outer layers drift away into space, forming an expanding cloud of gas around the star. As more material is lost, eventually the star's hot, naked core becomes exposed, illuminating the receding layers from within. The Sun will no longer be a red giant, but a small, incredibly hot star at the center of a growing gaseous shell. What forms is one of the most beautiful phenomena in astronomy, a planetary nebula. Despite the name, a planetary nebula has nothing to do with planets. The term arose because through early telescopes, these round gas shells looked a bit like planetary disks. It is the glowing remnant of a star's atmosphere, cast off into space. The emerging stellar core at the center may be tens of thousands of degrees hot and emits strong ultraviolet radiation. This radiation ionizes the expanding shell of gas, causing it to fluoresce in vibrant colors, soft greens and reds from oxygen and hydrogen, for example. Planetary nebulae come in many shapes: spherical shells, ring-like structures, hourglass forms, even complex symmetrical patterns sculpted by magnetic fields or binary companions. They last only tens of thousands of years before the gas disperses into the interstellar medium. But while they shine, they are among the most beautiful sights in the cosmos, the very soul of a star laid bare in color and light. Our Sun's planetary nebula might appear as a shimmering halo in the sky, a final gorgeous adornment to mark the end of the Sun's life as a star. This nebula will expand and dissipate into the interstellar medium over perhaps 10 or 20,000 years, mixing its enriched gases with the cosmic clouds that will someday form new stars. At the center of the planetary nebula remains the core of the star, a dense, hot sphere about the size of Earth, composed mostly of carbon and oxygen. This is the final state of the star, a white dwarf. A white dwarf no longer has fusion occurring in its core. It is supported against further collapse by quantum degeneracy pressure of electrons, a rather exotic form of pressure that doesn't depend on heat. When it first forms, a white dwarf is extremely hot, well over 100,000 K, and it glows white-blue with residual heat. Over billions of years, it will radiate that heat away and cool down, becoming yellow, then red, and eventually fading to black, an exotic cold crystal of carbon and oxygen in the far future, sometimes poetically likened to a giant diamond in space. However, the universe is not old enough for any white dwarfs to have cooled to the black dwarf stage yet. Even the oldest white dwarfs still shine faintly with leftover heat. The white dwarf that remains of our Sun will be incredibly dense. More than half the Sun's mass is crammed into a sphere the size of Earth. A single teaspoon of its material would weigh billions of kilograms. It's an object not unlike a planet in size, yet containing the mass of a star. It will slowly cool and dim, perhaps taking tens of billions of years to become truly dark. In the meantime, the legacy of the Sun lives on. The planetary nebula it ejected enriches the galaxy with elements like carbon and nitrogen that were made in its core, and the white dwarf stands as a testament to the star that once was. This is the gentle end that awaits stars of modest mass, a quiet shedding of beauty and a final fade into darkness. But what of the giants? The massive stars that lived only a few million years on the main sequence and then grew into supergiants. They face a far more dramatic end. A star significantly heavier than the Sun, say 8 times the Sun's mass or more, will go through similar stages, hydrogen to helium, helium to carbon, and so on, but it doesn't stop at carbon. After the red supergiant phase begins, its core, much more massive than the Sun's ever was, keeps contracting and heating. It ignites carbon fusion when helium is depleted. Then it forms a core of oxygen neon magnesium, which in turn, when exhausted, leads to neon burning, producing oxygen and magnesium. Then oxygen fuses into silicon and sulfur. Finally, silicon burns into iron. The star develops onion-like layers. At the center, an iron core. Around that, a shell of silicon fusing to iron. Above that, a shell of oxygen fusing to silicon. Then a carbon-burning shell. Then a helium-burning shell. Then a hydrogen-burning shell at the exterior. Each stage of fusion releases energy, except the last. And for a time, each supports the star. But the cycles accelerate. Carbon may burn for 1,000 years, neon for a year, oxygen for mere months, silicon for days. The iron core grows rapidly as silicon burning dumps iron ash into it. And then the star reaches the final limit. The iron core grows so large, around 1.4 solar masses, that it can no longer support itself. Iron is a nuclear dead end in a star's life. Fusing iron atoms doesn't yield energy, it consumes energy. So once the core is largely iron, the star has no further fuel to tap that can hold up the core. In the heart of the massive star, in the span of a second or less, everything changes. The iron core, about the size of Earth and incredibly dense, billions of kilograms per cubic meter, collapses under its own weight. Electrons and protons in the core are crushed together, forming neutrons and releasing neutrinos. The core's collapse accelerates until it is stopped by the most fundamental forces, the strong nuclear force and neutron degeneracy pressure. What was an iron core a few thousand kilometers across is now a ball of neutrons, only perhaps 20 kilometers in radius, a nascent neutron star. The infalling material of the star's inner layers crashes onto this incompressible core and rebounds. A powerful shockwave forms, but at first it stalls within the star. Then, aided by an immense flood of neutrinos pouring out of the core, trillions of neutrinos blasting through each square centimeter, depositing energy, the shockwave regains strength and punches outward. In a magnificent catastrophe, the star explodes. This is a core collapse supernova, the violent death of a massive star. In that instant, the star is obliterated. The outer layers are catapulted into space at a significant fraction of the speed of light. The energy released is almost unfathomable. For a few brilliant days or weeks, the exploding star can outshine the entire galaxy that once humbly hosted it. If such a supernova occurred within, say, 100 light-years of Earth, it would appear brighter than the full moon and could potentially wreak havoc on our biosphere. But typically, these explosions occur safely distant, turning up as new stars in the sky, recorded by astonished observers across history. In 1054 CE, Chinese astronomers recorded a guest star that remained visible in daylight for weeks. This was a supernova in our own galaxy. Even today, nearly 1,000 years later, we see the expanding debris of that explosion as a faint, glowing cloud in the constellation Taurus. In 1604, European observers witnessed another brilliant new star in the Milky Way, which was likewise a supernova. And in 1987, a supernova blaze in a neighboring galaxy, the Large Magellanic Cloud, was visible to the naked eye. These rare events left a deep impression on those who saw them. When the supernova's glare finally subsides, it leaves behind a rapidly expanding shell of gas and dust, a supernova remnant, and, at its heart, the crushed core, either a neutron star or a black hole, depending on the mass. The supernova remnant is a spectacular thing in its own right. The ejected gases, enriched with heavy elements forged in the final moments of the star, like nickel, cobalt, and iron, rush outward and collide with the surrounding interstellar medium. They form glowing filaments and shock fronts that can remain visible for tens of thousands of years. Telescopes today reveal delicate tendrils and wisps of glowing gas in these remnants, beautiful and haunting, the ashes of a star spread across light years. These filaments gradually mix with the general galactic gas. The elements they carry, oxygen, carbon, silicon, iron, and more, become part of the raw material for new stars and planets. Thus, a supernova is both an ending and a new beginning. The star is gone, but its material is now free to join new cosmic structures, and even one day, to become part of new living worlds. At the center of a supernova remnant lies whatever remains of the star's core. If the progenitor star was not too extremely massive, perhaps up to 20-25 solar masses, this remnant will be a neutron star. If the star was more massive, The core collapse likely continued until a black hole formed. Let us consider the neutron star case first. A neutron star is one of the strangest objects in existence. Imagine compressing the sun into a ball only 20 kilometers across, the size of a city. At that density, a single teaspoon of neutron star material would weigh billions of tons on Earth. The gravity at its surface is so intense that if an object were dropped from 1 meter above the surface, it would hit the surface in a microsecond, releasing as much energy as a large bomb. Yet, despite these extreme properties, neutron stars are real, and we detect them regularly. Many neutron stars reveal themselves as pulsars. When a massive star's core collapses to a neutron star, it often retains much of its rotational momentum in a greatly shrunken form, so it spins extremely fast. Imagine a star spinning once every 30 days, like our Sun, collapsing to an object only 20 kilometers wide. Conservation of angular momentum would make it spin perhaps hundreds of times per second. Indeed, many neutron stars spin at least dozens of times per second when born. They also can have intense magnetic fields, trillions of times stronger than Earth's. These magnetic fields, anchored in the dense star, accelerate particles and create beams of radiation from the neutron star's magnetic poles. As the neutron star spins, these beams sweep around like the light from a lighthouse. If Earth lies in the path of these beams, we observe a pulse of radio waves, light, or X-rays with each rotation, hence the name pulsar. Some pulsars spin with astonishing speed. A millisecond pulsar can rotate over 700 times in 1 second. Their regular flashing is so precise that pulsars rival atomic clocks in stability. They are nature's metronomes. When pulsars were first discovered, their signals were so regular that some jokingly labeled them LGM for little green men, suspecting an intelligent origin before natural causes were understood. Now, pulsars help us probe extreme physics and even detect gravitational waves indirectly through changes in their orbits. A lone neutron star will gradually cool and slow down over millions of years, becoming fainter and less active. Some neutron stars have magnetic fields so strong that they occasionally fracture their own crusts in starquakes, producing bursts of high-energy radiation. These are called magnetars, and they are the most magnetic objects known. But even magnetars eventually calm as they lose energy. In the fullness of time, a neutron star might become a cold, inert sphere of neutron matter, drifting through the galaxy. Yet it will remain, essentially forever, as a remnant of its parent star, a cosmic tombstone marking where a mighty star once shone. If the core of the collapsing massive star was above the neutron star limit, around 2-3 solar masses, gravity wins an even more final victory. The core continues to shrink past the neutron star stage and becomes a black hole. This is the most extreme outcome of stellar death. The entire mass of the core collapses to an infinitely small point, as far as our physics can describe, and a region of space-time is created from which nothing can escape. A black hole is not a solid object, but rather a region, bounded by the event horizon, beyond which escape velocity exceeds the speed of light. Whatever remains of the star's core resides in that region, forever cut off from communication. In effect, the star's mass punches a hole in the fabric of the universe. All we can observe is the gravitational field it leaves behind, and perhaps X-rays or jets from materials spiraling into it from outside. If the black hole is alone, it may be nearly impossible to detect, as it emits no light of its own. But if it has a companion star or is surrounded by gas, that material can form a hot accretion disk as it funnels into the black hole. Friction and extreme gravity heat the disk to millions of degrees, causing it to glow in X-rays. Sometimes, as the disk material swirls inward, the black hole's magnetic and rotational effects can launch jets of particles at nearly light speed from the poles. These relativistic jets can extend for light years, a ferocious announcement of a black hole's presence. Yet, despite such displays, the black hole itself remains unseen. Only its influence on nearby matter and spacetime is evident. It's a silent well in the fabric of reality, a gravitational ghost marking where a star once radiated. In either case, neutron star or black hole, the core collapse supernova has transformed the star and distributed almost all of its substance back into the cosmos. And that is perhaps the greatest significance of these mighty events. They are creators in destruction's clothing. In the furnace of the supernova and in the neutron star mergers we discussed, many of the universe's heaviest elements are forged. The gold in your jewelry, the iodine in your thyroid, the uranium in the Earth's crust. These atoms were synthesized in the intense crucibles of exploding or colliding stars. The calcium in your bones was formed in a long-dead red giant. The iron in your blood was made in the core of a massive star and distributed by a supernova. Stellar lives and deaths are directly responsible for the elemental richness that enables planets and life. Without generations of stars cooking simple hydrogen into heavier elements and then ejecting them, a planet like Earth could never exist. The universe's first stars had no solid planets around them. There was nothing solid to form rocks or life. It took billions of years of alchemy in stars to brew the ingredients of biology and geology. Thus, each generation of stars leaves a legacy for the next. The gas between stars, the interstellar medium, grows increasingly enriched. Young stars that form now have subtle amounts of iron, silicon, oxygen, and other elements mixed into the primordial hydrogen and helium because they draw from clouds seeded by prior supernova and stellar winds. Our Sun, for example, contains about 2% of these heavier elements, metals in astronomer speak, whereas a first-generation star had virtually none. That 2% might sound small, but it's critical. It's the material that formed Earth and our bodies. In a cosmic sense, later stars carry the DNA, so to speak, of earlier stars within them. Every star that dies writes part of its story into the next generation's composition. We see this continuity everywhere. In regions where massive stars recently died, we often find new star formation triggered by their explosive energy, like flowers blooming after a forest fire. The shockwave from a supernova can compress nearby clouds of gas, spurring those clouds to collapse into new stars. The intense radiation from young hot stars in turn can erode and sculpt neighboring clouds, sometimes stimulating further clumping and star birth at the cloud's edges. It's an intricate cycle, star death leading to star birth, a cosmic phoenix rising from the ashes. Through this ongoing cycle, the galaxy's supply of gas gradually diminishes, but it ensures that successive generations of stars are born with the gifts of their ancestors already inside. By now, it's clear that stars are not isolated points of light. They are the central actors in the great story of the cosmos. They sculpt galaxies with their collective light and their winds and explosions. They forge nearly every chemical element heavier than helium in their cores or in their fiery deaths, and they create the conditions for planets to form around them in the leftover disks of their birth. From those planets, beings like us can eventually emerge, beings made of star stuff, who then look back and ponder the stars. Our Earth coalesced around a second or third generation star, the Sun, about 9 billion years into the universe's timeline. It carries in its rocks and living organisms the fingerprints of countless stars before us. The silicon in the sand, the phosphorus in our DNA, the sodium and chlorine in the oceans. Those atoms were fashioned long ago in stellar furnaces and then scattered across space, eventually to become part of this planet. The heavy elements from bygone stars now circulate in our blood and build our cities. We truly are a way for the cosmos to experience itself, as one great scientist put it. When we gaze at the stars, we are literally seeing our own origins. The light from those distant suns allowed Earth to form and life to develop, and now our eyes capture that light and our minds understand it. We have closed a loop in a sense. The stars made us, and we, in turn, can comprehend and appreciate the stars. It's a humbling and uplifting realization that underscores the unity of everything in the universe. As our journey through the lives of stars comes to an end, picture yourself once more standing beneath a clear, dark night sky. The silence of the night is profound. The only sounds might be the wind or a distant owl. Above, the stars sprinkle the heavens with their gentle light. The Milky Way arches overhead, a faint band made of the amalgamated glow of billions of distant stars. With the knowledge we have gathered, each point of light now carries a story. You can point to a star and think, that might be a middle-aged star like the Sun, with planets orbiting it and perhaps life of its own. Another might be a massive blue giant destined for a short, brilliant life and a dramatic supernova end. That red one there could be a giant star in its final phases, about to shed its husk and reveal a white dwarf. Yet another faint smudge might not be a single star at all, but an entire galaxy far beyond our own, filled with hundreds of billions of stars, each with its own journey. In the stillness of such a night, the weight of this understanding can be awe-inspiring. We stand tiny on a small planet, bathed in the ancient light of stars, connecting us to epochs and places we will never see. The stars evoke not just scientific curiosity, but also a deep emotional response. For thousands of years, humans have looked up in wonder, weaving myths and seeking guidance from the stars. In ancient times, the night sky was humanity's map and calendar. Farmers planted and harvested by the rising of certain stars. Sailors navigated by the star patterns, and every culture filled the sky with stories, images of bears, hunters, dragons, and heroes that gave meaning to those distant lights. The stars have always been our companions in the dark, symbols of permanence, even as we now know they too have life cycles. Now we have peeled back many of their secrets, yet the wonder remains, and has perhaps only grown deeper. We know that those stars are not eternal. They are born, they age, and they die, in an endless cosmic cycle. We know that on some nights, some of the stars we see have already died in reality, but their light is still on its way to us, a messenger from the past. We know that every atom in our body was once inside a star that died long before Earth formed. We are intimately connected to these points of light. They are our stellar ancestors, and in a real sense, we are their children. Such knowledge does not diminish the star's beauty, it amplifies it. When we look up now, we see not just pretty lights, but a grand story unfolding across the vastness. Eventually, even the stars will fade. The universe is dynamic and evolving. Trillions of years from now, the galaxies will exhaust their gas, star formation will cease, and the remaining stars will gradually die out. The cosmos will go dark again, as it was in the beginning, but now filled with the remnants of those stars. White dwarfs turned cold and black, neutron stars, and black holes roaming the darkness. But that far future is almost beyond contemplation. Right now, we live in a universe awash with starlight. It is the golden age of stars, where new ones still form and the night sky still gleams. We are fortunate to witness it, and as long as there are eyes to see and minds to wonder, the stars will never be merely points of light. They will be beacons of meaning, symbols of the enduring cycle of creation and transformation. Stars are the ancestors of everything we know and the architects of the universe's structure. They crafted the elements that form our world and our bodies. They organize themselves into galaxies that shape the cosmos on the grandest scales. As we conclude this meditation on stars, we find ourselves back in silence, contemplating the darkness that is now no longer empty. It's filled with the gentle glow of distant stars and galaxies, a cosmic tapestry woven by countless suns. In the great silence of space, the starlight we see continues to journey outward. Even after a star has lived its life and gone, its light remains, traveling through the darkness, carrying the tale of that star's life to faraway places. Right now, above you, photons from stars hundreds of light years away are gently landing on your eyes, having left their homes long before you were born. And those photons will continue past you into the night, on an endless voyage. The universe is silent, but it is not empty. It is filled with the stories of stars, whispered in the language of light. And so we end where we began, with darkness and quiet. But now we know that in that darkness, light is always traveling. The stars, our brilliant ancestors and cosmic architects, shine on, and in the quiet darkness, their light continues its eternal journey. In the silent darkness of space, their starlight continues to travel, carrying their story across the cosmos forever.